used in the biology applications. So, but it will be essential to learn. Good morning, all of you. Yeah, today's talk is about introduction to biomaterials, structure, function, relationship. So here, as you can see, biomaterials, like bio is in a small word, a small font, and the materials in the larger font. So mostly we'll be talking more about the materials, very less about the biology. The scheme of the presentation is structure property relationship of the materials, broad classification, so concept of defects. So you cannot like make the material without defects. So you need to know the nature of the defects and how this defect can be utilized in toughening. And also based on the different structure property relationship, we'll discuss how the materials property manifestation from the structure and function. We'll be discussing about the classification of the materials, like different metallic materials, polymeric materials, glass, ceramics, sometimes people call glass ceramics. Then also we'll discuss about the SB diagram for the modulus and strength of the materials. And I think we already have learned the stress shielding and the Wolff law, and how we can design the materials to reduce the stress shielding, and of course porous implants and different functionally graded materials. Yeah. So as you can see, this diagram, what you can see, there is a structure. I think it's not very clearly visible. Structure. So I think all the materials has the structure, and according to the structure, they have their own properties, and also the structure properties. And when you make the components, you have to follow a process. When you make a component, you have to follow a process, right? For example, if you have to make a glass, this is a glass, right? So this is a glass. So when you are making a glass, you have to melt, right? And if you are making like a ceramic components, you are making a compact, and then you are sintering to make the safe. So there are different procedures for making the safes. There are different top down and bottom up approaches for making the safes. So when you are making the safes, you cannot avoid the defects. So that is why the processing condition and the specific process has a major role to play for, or is a decisive factor for the property of the materials as well as their performances. So that is why unless we study the structure, property and the processing relationship, we cannot draw a conclusion on the performance of the material. So as you know that materials are very diverse and has huge applications from microelectronics, infrastructure, environmental control, communication, information, energy, automotive, defense. Of course, we'll be talking about biomedical and sporting goods. So as you talk about biomedical, there also you will see, even we already have gone through several lectures, that the materials, even the hip joints or knee joints, as you talk about, some portion of the implant are bioactive in nature, and some portion of the implants are absolutely mechanical, uh, mechanical function they have. So that is why when we are designing a material, so we need to consider the exact function and the location, and accordingly we need to decide the materials. So for that we need to know the properties of the materials. So of course, as I said, the biosensors is one of the important area in the biomedical. We know the implants, we know drug delivery systems, even we know the tissue engineering scaffolds where the materials are transient materials. We deliver the materials, it stays for some time and then it disappears with time. So that is why it is important to know the structure, function and performance relationship, and all these depends on the processing parameters as well as the processing conditions, and during the processing there would be some defects, we need to consider those as well. So as we know the structure, I think this is almost we can say secondary or school subject, this slide mostly. So as you know, any of the materials are composed of atoms. So there could be many different type of atoms, and atoms arranged together to form the molecules, right? These molecules can arrange in a regular fashion to make it crystalline, or they could arrange in a random fashion to make it amorphous, or even they can be much longer chain, which is the case for the polymer, or these chains can be interlocked by cross linking. These chains can be interlocked by cross linking, okay, and there could be defects during the processing, or there during the extraction, or during the synthesis, and there could be impurities. So you cannot avoid the defects and impurities. In case of crystalline material, you have the grains. So these grains are the units of the material. For example, if you look at the buildings, in the buildings, what are the units? Bricks, right? So bricks are the unit. So similarly, in case of materials, you have grains. Similarly, in case of say, tendon and collagen, for example, we know what are the units? Collagen molecules. They are assembled to form the fibers and fascicles. So that is why the hierarchy structure is very, very important. And as we know, the unit cell or the building blocks should have minimum defects. That is very, very important. And in the unit cell, if we minimize the defects, and of course we have the materials which has minimum defects. That is our target. So as you see that atomic bonding has the dimensions in the order of 10 to the power minus 10 meter. Missing or extra atoms also in the order of 10 to the power minus 10 meter. The crystals can be very small, could be like 10 to the power minus 10, 10 to the power minus 1, 10 to the minus 8 to 10 to the power minus 1 meter. The second phase of particles could be in the order of 10 to the power minus 8 to 10 to the power minus 4 meter. The crystal could have different type of textures. These textures could be in the order of 10 to the power minus 6 meter. So you cannot avoid the extra atoms, the crystals, or the second phase particles. So this is part of the structures. So you have to understand this texture, second phase, inclusions, defects, missing atoms, right? And as you can see that grains, So as you can see that, and grain boundaries. So as you can see that all these structures are of different orders, okay, different orders, different sizes. So I think we know the materials has mostly two type of bondings. One is called covalent bondings, another is ionic bondings. So as we know, the electronegativity difference is a major driving force for this different type of bonding. So can you tell me a perfect covalent bond in a material? A perfect covalent bond in a material? Any materials, right, having same atoms, and if they are like other than metal and metal oxides, so like carbon, for example, carbon carbon, nitrogen nitrogen, oxygen oxygen, so they are perfect covalent bonds because there is no electronegativity difference, and if the electronegativity difference is less than 1.7, so it is covalent. And then if the electronegativity difference more than 1.7, then there is a special character called percent ionic character. So if it is about 1.7, then it is about 50% covalent and 50% ionic. If this bond has electronegativity difference more than 1.7, so this is called ionic compound. So interestingly, the covalent bond has the bond length in the order of about 0.15 nanometer, and they are having very strong bond energy in vacuum as well as in water, right, in vacuum as well as in water. And ionic bonds has the bond length is about 0.25 nanometer. They are also very stable in vacuum, but they are least stable in polar solvent because there is a possibility of solvolysis. There is a possibility of solvolysis. There would be ionic interactions that could cause leaching of the ions into the aqueous system. So other than covalent and ionic bonds, there are non-covalent interactions like hydrogen bonding, van der Waals forces, as well as London forces. We know the London forces are the major driving force for attractive forces in the inert gases. So as you can see, the hydrogen bonding is also stable in vacuum, but in water it reduces to 1 kilocalorie per mole. Van der Waals force is having very similar bond energy in vacuum as well as in water. So based on all these bondings, right, so there are molecules. I think we must be knowing the molecules. Can you give any example of a molecule? A molecule like water, carbon dioxide, right? So these are molecules. So similarly, if you say sodium chloride, sodium chloride is a molecule? So if you see, sodium chloride are in the network. So there are alternate structure of sodium plus, chloride minus, sodium plus, chloride minus. So that type of 3D network is there. So that is called molecular network. Similarly, in case of metals, it is most likely that individual metals and individual metal atoms are not very stable. They form the metallic bonds, right? And all the metals are also, metal atoms are also assembled in a 3D network. Similarly, if we have a carbon dioxide, for example, is a stable individual molecule, but sodium chloride is not really a stable individual molecule, rather they are in a network of ions, and that is why called molecular network. But whereas silica is also a covalent molecule, but because of silicon and oxygen very poor overlapping for sigma bonding or double bonding, sorry, so they make the 3D network structure, 3D network structure of the covalent bonds, right? So that is why silica is also a molecular network composed of covalent bonds. So silica is a 3D network of covalent bond. Sodium chloride is a molecular network of ionic bonds, whereas metals are also a molecular network of metallic bonds. Clear? So that is why you see very different properties. You see, that is why very different properties. Similarly, the sodium chloride, when you add into water, what you get? Ions are there in the water. So that is called ionic solution. The same sodium chloride, when it is melted, it is called ionic liquids. Okay, so that is why we have very different properties. This long chain polymers, for example, as I am saying, the molecular network of silica, molecular network of ethylene, make it polyethylene. So lot of ethylene molecules are combined to form molecular network, right? When these chains are too long, it is not very easy to handle them. They eventually have the tendency to entangle, right? As you see that they can easily entangle. They can easily entangle, right? So if they can easily entangle, the property we get because of molecular entanglement. So most of these polymers, I think most of these polymers we see, fibers, this is also a polymer, this is also a polymer. I think you must be recognizing this. What is this? Acetabulum, made of ultra high molecular weight polyethylene. So this property is solely because of molecular entanglement, whereas in case of sodium chloride it is because of ionic interactions and the molecular network, and in case of metal is because of metallic bonds, right? So this has to be very clear. So as we know that silica has covalent bond, right? Silica has covalent bond, and of course they have a network. So quartz, silica quartz is a solid. Silica quartz is a solid. So this silica is quartz or glass. This is glass. So this is solid or liquid? So we'll see this is also a liquid, right? This is also a liquid. That is the, so this is not a quartz, this is a glass. So glass synonymous to liquid. But then if you see a glass of water, if you see glass of water, right? So you see there is a silica glass and also we have water in it. So both are liquid. Then what is the difference? Can you make out? Pardon? Both are liquid, physical state. Density depends on their individual properties. Water has a different density. Then how they are different? How do you define? What is the physical property? One has very high viscosity, another has very low viscosity. So the silica glass is also flowing. If you go to the charts in European charts, so they have the glass doors which is there, and if you see on the top very thin, on the top very thick, because it is flowing, because this glass door is there for thousands of years, so it is very slowly flowing. The flow rate is very slow because they are highly viscous, right? Clear? So quartz is solid, but glass is not solid, it is a liquid, or we call them supercooled liquid. Supercooled liquid. So water is a liquid eventually, the ice is a solid, Oxygen is a gas. We know sodium chloride is ionic, having molecular network. Metals have metallic bond, they are also having network, and there are carbon dioxide which are covalent and individual molecules are stable. Okay. So we know the polymers are actually giant molecules. Polymers are giant molecules. So if you consider the individual human, they have two bonds, two functional group, like two hands, right? So now if you make the human chain by holding, not by forming the dimer like putting two hands with another person, but instead if you just individually hold the hands and make a chain, huge chain, it is like a human chain. So similarly in case of polyethylene, so if you put many ethylene molecules together, so they form polyethylene. These are called gigantic molecules. So I think we know the cup. This cup is made of paper. So what is the paper made of? Pardon? Wood? Cellulose, right? Cellulose. Cellulose is made of glucose, right? So there are so many glucose molecules joined together forming cellulose. So this is called giant molecule. So how this structure is formed? Because entanglement of the fibers together forming the structure, and then you are forming into different shapes, and when we are forming the shapes we have to consider their properties. So based on the properties only we can make their shapes, right? Now if you look at the ionic compounds like sodium chloride, what is the melting point of that? Extremely high, because they are very tightly held, because they are ions, right? Similarly if you see the metals, they have the metallic bonds, right? Whereas the polymers, they are entangled. So if you increase the temperature, some of the polymers, they can melt, okay, they can become mobile, okay, and then gradually they melt, and when they melt we call them glass. So you can eventually make metallic glass, we can eventually make polymeric glass, or we can make ceramic glass. So the glass meaning it is a liquid, right? It doesn't have any repetitive structure in a long range, So glass can also have the 3D structure, but very short range structure. But in case of metals or ceramics or the polymers having high degree of crystallinity, they have very long range order. But whereas in case of glass you have very short range order, okay, clear? So these polymers are actually a giant molecule, right? So it could be linear, also it could be branched, isn't it? So suppose this chair is made of cross-linked polymer, right? Can you predict how many molecules are there? Pardon? Many, right? There even could be one molecule. So you can eventually see the molecules or one molecule. If it is a highly cross-linked product, there could be even one molecule, which is one chair is a one molecule. That is also possible, right? Okay. So we also have a hybrids and composites. What we do, we can mix two different materials to get enhancement in the properties of physical properties, okay, that is composites. Hybrids, when you are mixing metal with ceramic, ceramic with metal, or polymer with ceramic, or polymer with metal, so that is called hybrids. We are mixing two different materials, two different class of materials and forming the material called hybrid. And of course, the design is very, very important, right? Design is very, very important. So we can see the polymers has different class. I will not go into the detail of the classes, but I will just focus mainly on few classes which are important for our biomaterial studies. One is called synthetic polymer. Any example of synthetic polymer? Yeah, polyvinyl alcohol, polyethylene, polystyrene. Have you ever seen polystyrene? You have seen? Where? Polystyrene. You know this material, packaging material? Packaging material. This is polystyrene, right? You have seen ultramolecular polyethylene, synthetic polymer. We have seen silicon rubber, right? Or elastomer. This is also synthetic polymer. So this is also a polystyrene inside. Okay. So these are all polystyrene, synthetic polymer. Whereas if you see this polymer cup, it is cellulose, which is a biopolymer. This thread is made in our laboratory long back in 2007 or 8. So this is a polymer thread we actually spun into fibers. So these polymer fibers or threads are made of chitosan, which is shrimp or crab shell, which is a biological waste material. So which we can dissolve them and we can spin them into fibers for different applications. Is it okay? This is a biopolymers. Any other example of biopolymers? Can you look at? Whole body is made of biopolymers other than minerals, isn't it? Collagen, as I said yesterday, there are 29 types of collagen. Just recently they have discovered one more. So 29, it was 28. So 29 types of collagen. So all are biopolymers. Hyaluronic acid, biopolymer. GAGs, glycosaminoglycan, biopolymers. Proteoglycans, biopolymers. Keratin, biopolymers, right? And if you can mimic the structure, then you have done the wonderful job. And that is our target, but it's not very easy, right? Clear? So the synthetically the polymers you develop by synthesis in the laboratory, that is called synthetic polymers. Polyester, for example, polyester cloths. Polyester is a synthetic polymer. Nylon is a synthetic polymer. Polylactic acid is a synthetic polymer. Okay. Polycaprolactone is a synthetic polymer. Polyethylene glycol is a synthetic polymer. Polyvinyl alcohol is a synthetic polymer. Can I give an example of polyvinyl alcohol you use every day? PVC is a polyvinyl chloride, PVC pipe. Polyvinyl alcohol is used in Fevicol. This is nothing but water solution of PVA. And have you used the Fevikwik? Fevikwik is also a synthetic polymer. What is that? Polyacrylonitrile. What is written there? You should use very carefully, right? If it goes to the eyes, so it can join. So what is the application? Soft tissue adhesive. Simply it joins the skin. So it directly can be used for soft tissue adhesion. Okay. So these are the different polymers, synthetic polymers. So there are biopolymers, as I said, collagen, hyaluronic acid, cellulose, hemicellulose, lignin, polyhydroxybutyrate, polyhydroxyvalerate, different proteins, many different type of proteins are there. Human body has more than 1,000 different type of proteins or more. And also semi-synthetic polymers. So we also sometimes modify the polymers to make it more tailorable for different applications. I think if you might have read the story of vulcanization of the rubber. So rubber was developed, discovered, and they used for cycle tires. These rubbers in the winter season it is like a solid, but in the summer season it is like liquid. So you cannot ride the bicycle because rubber is liquid now. So you have to develop the process by which we can retain its physical properties or solidity as well as the elastomeric property. So for that, so they have explored many different ways, and very interestingly, one fine morning scientists found, so at the corner of the container, so it is cross-linked, it has different property. It is because the rat inside the house, they carried the sulfur, and sulfur somehow it fell down to the rubber and it cross-linked, so it vulcanized. So I think rat has done the job. So we borrow the idea and start doing it, and we get the vulcanized rubber, which is the most what you call commercially explored rubber today in our day-to-day life, or elastomer in our day-to-day life. Similarly, I think we know the casein. Casein is used for inside lining of the car. The casein is actually made of proteins, milk protein, and it is cross-linked by formaldehyde. Okay, so there was a container, formalin was there, and there was a container where milk was there. In the night, so scientist is sitting in home and doing different activities. Suddenly the power has gone, and I think cat or dog, I exactly cannot remember, it jumped, and the formalin bottle fell down into the milk. And next day morning they found it has transformed into the polymer. Basically it cross-linked, and then he got the wonderful properties. So these are the different discoveries led to today's all advanced application of polymers and the polymer science. So as I mentioned, we have ethylene. So if you join this ethylene one by one, we get polyethylene. So basically you see this is called vinyl, okay, vinyl group, CH2CH, one group is there. In this side group, if you put hydrogen, it is ethylene, then it is, if this ethylene you combine, so how many we can combine? Pardon? N number of how many? Any idea? How many? 100, 200, thousands, lakhs. So here also very interesting story. So polymer scientist trying to synthesize the polymers, and he's just sharing his knowledge with a friend that I am trying to synthesize the polymer, right? But I am ended up in a sticky polymers. So polymers like ethylene monomer, which is gas, when you make it polymer, as the molecular weight increases, so gas becomes sticky, then liquid to the sticky polymer to the solid. So that is why polymer scientists always try to do one of the tests, whether solid becoming solid or not. So he shared the knowledge with his friend that I am trying to synthesize the polymer, it is having very sticky nature, right? Sticky nature. So when he shared this knowledge, his friend has used this idea, and what he did actually, he just put in a yellow paper and he became billionaire, because you know yellow paper today, sticky, is used for writing the notes. So even if the low molecular polymer can be used for different applications, so cleverly he has used this yellow paper using low molecular polymers, right. So this is a ethylene, which is gas, you combine together you get polyethylene, and you have, as I said, vinyl group, vinyl chloride, you get polyvinyl chloride, PVC. So you remember just 20 years back or 15 years back, all the pipes were made of I think mostly the crockeries like clay, and then metallic was there, and gradually all replaced by PVC nowadays. So propylene, then you have polypropylene, wash bottles, in the laboratory bottles we use, hard bottles are polypropylene, soft bottles are polyethylene, and we have polyvinyl acetate, which is this acidic group, is when you hydrolyze we get polyvinyl alcohol, and we have vinylidene chloride, we have polyvinylidene chloride, we have Teflon. You see, just ethylene when it is fluorinated, right, when it is fluorinated we get polyethylene. So this polyethylene is water repellent, it is fire retardant, it is not hard, it is water repellent, it is fire retardant, okay. So it is used for firefighter, for jacket, and also it is used for non-sticky cooking ware. You see today all the utensils, there is a coating, black coating is there, sometimes it could be anodized, okay, or sometimes it could be Teflon coated, okay, and this Teflon is water repellent and fire retardant. These polymers has very good blood compatibility, and that is why this polymer is also used for different blood related applications, okay. So styrene, you see, this is again a vinyl group along with a side group is what, benzene ring. So styrene, so because of this benzene ring, the main long chain polystyrene is very rigid because of this ring, and that is why, because it is rigid, it can be used for packaging. Simply it can be used for packaging because it is rigid. Why it is rigid? Because there is a benzene ring. Similarly, in the vinyl group, if you add also carboxylic and methyl, then it is called PMMA, polymethyl methacrylate. Do you know any application? So there is a lot of medical applications as well as all structural applications. Paperweight, for example, one of the easiest way to say. So paperweight, but polymethyl methacrylate is used as a bone cement, for example. One of the example, contact lens, hard contact lens, intraocular lens, hard intraocular lens, even the glass, okay. Acrylonitrile, polyacrylonitrile, as I mentioned, polyacrylonitrile is used as a soft tissue adhesive. So if you have a soft incision, just apply what, Fevikwik, job is done, okay. So similarly we have pinipalm. Pinipalm was discovered a couple of years back, and pinipalm has very good thermoresponsive property. So at 37 degree it is highly hydrophobic. What is the importance of 37 degree? Body temperature. So you can do the cell culture on hydrophobic surface, and at 33 degree, or if you just reduce to 35 degree, it gains more than 90% of the weight by taking the water. It becomes hydrophilic. Then this whole cell layer, which is confluent cells are there on the pinipalm surface, it will come off as a cell sheet. So this cell sheet you can stack together you can make tissue like structure. So this is a cell sheet technology. Lot of activities are going on around cell sheet technology for cardiac related regeneration and some soft tissue related applications, mostly in Japan and Australia, even China also. IPGMER, poly hydroxyethylene methacrylate. Just instead of this methyl, I am adding hydroxyethylene methacrylate, hydroxyethylene group. And this methyl group, because of this methyl group, it is hydrophobic, and when we are adding OH group, then it is becoming hydrophilic. And the same material like PMMA, we can use it for contact lens, we can use it for intraocular lens, and we can use it for drug delivery applications. But these lenses are hydrogel lenses. So these lenses you cannot keep it dry, rather you store inside the solvent so that it does not crack because of the drying, right. So these hydrogel lenses are porous. It also allow oxygen permeability, and that helps eventually to breathe to the cells, for breathing of the cells. So there is also a condensation polymerization. So previous one I discussed is addition polymerization. Simply I am adding the monomers and eventually there is no byproduct. Simply I am adding the monomers and I am getting the polymers called addition polymers, right. And if we get acetylene and if we combine together, we get polyacetylene, which is a conducting polymers, And today's LED, as you know, LED TV, LED display, and all this LED revolution is because of conducting polymers. Very, very cheap. Okay. So there is also a condensation polymer. Okay. So condensation polymerization depends on the functional group. We know ester bond formation, we know amide bond formation, we know ether bond formation. So all these is possible with elimination of a water molecule. So when you have amine and carboxylic group combined together, they form amide bond, like amino acids they join together form amide bonds, and eventually there is a byproduct called water. So this is a condensation reaction, and with this condensation reaction we get condensation polymers. If these monomers have more than 2 amine or more than 2 carboxylic or amine and carboxylic together in the same molecule, we get condensation polymers. Is it clear? But now interestingly, if you see here in addition polymer, what is the polarity? The bond, nature of the bond, person ionic character, covalent, and here we have some person ionic character. That is why these polymers usually are not biodegradable. Whereas the polymers which are condensation polymers, because they have polarity, they are sensitive to water, acid, base, and that is why they are degradable. Could be biodegradable if they are degraded by some biological means. Okay, clear? So there are plenty of biodegradable polymers: polyamides, polyesters, polyethers, and polycarbonates. Even nylon, Kevlar, you know Kevlar, right? For making the bulletproof jackets, Kevlar is used, polymers. Okay, pteryline, that is also a condensation polymers. Polyethylene glycol, polycaprolactone, polylactic acid, polyglycolic acids, polylactic glycolic acids, polyhydroxybutyrate, which is synthesized by the microbes. It's a very good polymer. People are trying to increase the yield, and it can have one of the major applications would be for load bearing applications, and it's biodegradable. Nylon 6 we know very well, nylon 6,6, polyurethane and PET. Do you know PET? So what is this polymer? Do you know this polymer? You have used, pardon? Yeah, it can be used for packaging, as you can see it was used for packaging. So what is this polymer? Polyurethane. Okay, polyurethane. Similarly, there could be some other polymer. Yeah. What is this polymer? This one? PET. PET, polyethylene terephthalate. PET, polyethylene terephthalate. So this is a polymer. If you can, I think you have played in your childhood. Like we take the refill, we put on the flame, and you just pull. You get the fibers. So that is one of the method to make the fibers, right? This is one of the method to make the fibers. Simply take these bottles, just make it hot. So you get melt, and then you just pull it, you get the fibers. So these PET fibers are used for making heart valves, blood vessels. This simple, these materials are used for making heart valves as well as the blood vessels. Okay, and these polymers are biodegradable. Okay. Then we know different biopolymers: chitosan, hyaluronic acid, chondroitin sulfate, alginate. So chitosan is used as a wound dressing material. Hyaluronic acid, anyway, it is part of the extracellular matrix. Chondroitin sulfate is also extracellular matrix. We know in case of osteoarthritis, I think hyaluronic acid or chondroitin sulfate injection is also prescribed by the doctors, right? Yes. And alginate, which is also extracted from seaweed, okay. This alginates is a biopolymer and has a wound healing efficacy. This alginates, I think if you see that a lot of people also eat, they boil the milk and they eat, and this alginate also used for drug delivery application, wound dressing materials, and also it is used for live cell delivery applications. Live cell delivery applications. And these polymers can also be cross-linked different ways to tailor their properties for different applications. And I can tell you one important thing, that when you are doing the condensation polymer, as I said, in the monomers you should have at least 2 functional groups, whereas in case of addition polymer you should have at least 1 functional group. Okay, but in case of condensation polymer, if you have more than 2 functional groups, it eventually gives you cross-linked product, right? It gives you cross-linked product, and moreover, it is not very easy to carry out the reactions, polymerization reaction. So that is why usually the synthetic polymers has very limited functional groups for post modification and tailoring, whereas the biopolymers, as you see here, they have lot of functional groups for post modifications, and that is where the importance is. So we can use these polymers for diverse application by tailoring their properties through different cross-linking reactions as well as modifications. For example, I mentioned yesterday that RGD is the small peptide cues, which is recognized by the cell surface receptor integrin. Simply, if I take this small RGD and if I can cross-link to this molecule, it becomes bioactive. They behave like extracellular matrix. Okay, so that is fantastic, and so that kind of material can be can be strategically placed for increasing cellular activities. Okay, so we have metals, and we know metal has metallic bonds, and it is a molecular network again. Ceramics, which is having ionic bonds and is also a molecular network. And interestingly, whether it is a polymer or ceramics or metal, all are could be crystalline, could be amorphous, or could be having both crystalline and amorphous property, or called degree of crystallinity. So if we perform the XRD, we can see that amorphous material has this kind of straight line or hump, whereas the crystalline material will have this kind of sharp peak when we are drawing intensity versus 2 theta. Clear? And as you see, the crystalline material has extended 3-dimensional arranged or order structure, but for the amorphous material we have short range order, but in long range there is no not extensive order. I mean, order is very restricted. And also it is important to mention that crystalline material are highly anisotropic. Along x, along y, and along z direction, the expansion coefficient or any other properties will be different for crystalline material, but whereas for amorphous material these are highly isotropic. Can you tell me some anisotropic property of our tissues? Any one of the tissue? Bone, for example, highly anisotropic. So what you can see here, this is a glass. It doesn't have grain boundary, it doesn't have crystallinity, which is amorphous, whereas the crystals, as you can see, there are grain boundaries. Okay, there are grain boundaries, and in case of amorphous material there is no grain boundary. But in case of metals, we can tailor them into highly crystalline, or you can make them amorphous. Similarly, ceramics also, you can make them amorphous, you can make them crystalline, but depending on the cooling rate. Similarly, so as you can see that there are crystalline solids. So if it is single crystal, there is only one grain boundary, right? Whereas in case of polycrystalline material, there are many grain boundaries. And now you have to consider these grain boundaries are like defects. These grain boundaries are like defects, right? So if you can make a material which is single crystal, so you minimize the defects. Eventually we enhance the mechanical properties because defects are minimized. So for example, turbine blades, which is used for aero engines, they usually make single crystal turbine because to minimize the defects. Okay, so I remember Arthur Ware, I have gone through some paper. Arthur Ware mentioned that I can make a material of infinite strength. How? If you can eliminate the defects. If you can eliminate the defects, you make the material of infinite strength. Whereas the amorphous material, which are isotropic, there is no grain boundary. In case of single crystal, you have only one grain boundary, which is outside the wall. Whereas for polycrystalline material, you have many grain boundaries. Okay, and also there could be some other type of defects, point defects and line defects and 3-dimensional defects. Interestingly, in case of polymers, we have both crystalline and amorphous joined together. So usually it is difficult to achieve 100% crystallinity in case of polymer. So usually in case of polymer, if you can attain the degree of crystallinity more than 50%, we call them crystalline polymers, right? And in case of polymer, if you can attain the degree of crystallinity less than 50%, we call them amorphous polymers. But usually if you look at the structure, so polymers has degree of crystallinity, and there will be some crystalline zone, there would be some amorphous zone, and they are there. So amorphous zone, like this amorphous zone, are like a glass, and crystalline zone are like crystals. So that is why in case of polymers you have two type of temperature. one is called glass transition temperature and another is called melting temperature. So if you need to process the material, if you simply increase the temperature above glass transition temperature, then it is become soft, that is called softening temperature, and you can elongate them, you can process them. And if you go above melting temperature, whole structure has broken down, there is no crystalline zones and they eventually flow. So you can pour into the mold, you can inject into the mold and you can make different structures. Is it clear to all of you? I think this is the last slide. So as you can see now, so this is a polycrystalline material, you have lot of grains and grain boundaries, is it clear? And in case of fracture surface of the polycrystalline material, you can even see the individual grains, and there could be intergranular fracture and there could be transgranular fracture. What is our role? Our role is to minimize the defects so that materials property has enhanced. And there is a cartoon of three-dimensional polycrystalline materials, and the glass, for example, if you see quartz, which is crystalline material and it has a three-dimensional order structure, but in case of glass it is a three-dimensional structure but order is in very short range, and that is a amorphous. So I mentioned to you a glass of water, both are liquid, one has very high viscosity, another has very low viscosity, but both are liquid. And glass doesn't have any grain boundary, polycrystal has many grain boundaries, okay, and grain boundaries are also like a defect. I mean, it's not a defect, but you know, grain boundary is important, and also you cannot avoid the grain boundaries, and grain boundary also sometimes help the crack to deflect at different directions. That is important. I will discuss in the next class. I think I can stop here.
Hello, hello. Yeah, good morning, everybody. This lecture is on experimental validation of preclinical analysis, and we'd be covering different methods of experimental validation that those are required to validate a finite element model, which are again used for different investigations of clinical failure. Now, finite element analysis has been extensively used to test and validate clinical processes, in particular preclinical evaluations of orthopedic implant performance. Okay, so there has been different designs, different makes, different materials, and these are mostly preclinically tested using finite element method. Okay, so finite element models are generated and they are solved, and there's a sort of a numerical technique which actually predicts stresses and strain. However, the accuracy of the predicted stresses and strain depend on the quality of representation of the finite element model as compared to the actual situation. Okay, so there is always this very important question: how valid is your results? How valid is your predictions? So, an assessment of the validity of the FE predictions is required before the FE model can be further used for clinically relevant investigations. This is a very, very important message for all the researchers in biomechanics field. Now, there's been several methods for experimental validations, but one of the major method is the age-old robust strain gauge technique. Okay, you know, everybody in mechanical engineering perhaps knows what is strain gauge, and I think you have also performed experiments in the lab with strain gauges. The experimental measurements using strain gauge technique has often been employed to validate FE models of intact and implanted bone structure. Okay, if you see the literature, you will often see that there has been a lot of investigations. However, the strain gauge, as you know, yields discrete data. Okay, and it is an average of the real strain. It's an average value of the real strains occurring underneath the gauge. Okay, so there are strains at different location already within the gauge, just underneath the gauge, and then you actually average all the values of the strain underneath the strain gauge, and it is a discrete value. So local surface preparation instrumentation connected to the gauge as well as the temperature change might affect or can affect strain measurements. Okay. Now we have performed several experimental investigations in our laboratory to validate our finite element model. Again, we have employed actually composite bones, which are analog bone models of the femur, say for example the femur. But these analog models or composite femurs are representative, and it is not actual femur. not a cadaveric femur as well, but it's a representative femur, and these femurs are a specialized product of some companies, and it is quite expensive. So this has a outer cortical shell layer of glass epoxy fiber, and inside there is polyurethane representing the cancellous bone structure. But remember, this is not exactly the real life bone. Now, these are examples of some of the strain gauge fixation, as you can see on the left, on the femur, neck, also in the diaphysis of the femur. There are several strain gauge locations all over the femur. You can see here more clearly. And apart from strain gauges, we have also fixed LVDTs to actually track the implant bone micromotion, the relative displacement when it is being loaded. Okay, so this is two orthogonal direction. We have an extra additional sort of LVDT which is measuring the movement of the stem inside the implant bone structure. So there's a threaded hole, and inside we have put the peg so that any small change in displacement will be electrocanonically transmitted into recordings. There is a design, a newly designed and fabricated loading mechanism to actually mimic the hip loading, so which can be schematically represented like this. You can see that there is, when you apply the load, there are roller bearings on the two sides and along two directions, and it is actually sort of moving like a natural femur. So here the loading mechanism have been fixed on the machine, and we are testing an intact femur. You can see already strain gauges mounted on that, fixed on that, and then we are also testing the implanted femur. Now comes the important thing, the results. So as a researcher, you should be very critical about your finite element model. Okay, this is the first thing. So finite element strain at locations of the strain gauge needs to be computed, and you have the measured strain on the other hand. These raw data should be compared at corresponding locations. When you compare this, you will actually get the scatter diagram of how much deviations are there between the FE predicted strain and the actually measured strain by the strain gauges. Okay, so we have performed that for the intact femur, we have performed that for the resurfaced femur, and you can easily see from the figure that these symbols are actually strain gauge outputs for all the load cases. We have subjected the femurs to different load cases. So say starts from 700, 800, 900, goes to about 2 times the body weight. So about say 1500 or 1400. And this is quite a few number of data is now represented here. You can see there is a linear relationship already evident in the scatter diagram. Now what is this line passing through as a diagonal of this box? This is the ideal line, okay, which means that for a strain of 1000, FE predicted strain of 1000, you should actually get 1000 measured strain. But in sort of reality, we not always get that. So there is some deviations in the results which need to be also analyzed. So we perform a statistical analysis, the standard statistical linear regression testing of hypothesis, that how well is the FE predictions actually predicting the actual measurement. Okay, So we have a correlation coefficient, standard error of the estimates. We determine the slope. As you can see from the figure, that if it is a very good, excellent prediction, then the slope should be 1 and the intercept should be 0. Okay? But in actual, it never is. It is. Okay? So you can see that we have slope close to 1 and intercept close to 0. This is microstrain. Now I had plotted load versus strain curve. This is also very important when you perform experiments in your lab and try to publish your work. You must give the output of your strain gauges, different strain gauges. We have actually 8 strain gauges. You can see it is marked, and the sort of, as we increase the load, strain increases. This must be there as an output of your paper. This is resurfaced femur. Effect of stress shielding or strain shielding can be compared by comparing corresponding gauge locations, outputs of natural and resurfaced femur. So you can see here clearly that there is a natural case number 8 and there is a resurfaced case. Okay, so here the strain is higher. It's a compressive, more compressive strain. So, and it is lower in case of after implantation. The same is here. You can see the natural case number 2 strain gauge, and you can see that there is a substantial difference in the strain outputs after implantation, which basically symbolizes strain shielding. But remember, this is outputs measured on the surface of the bone specimen. Now we are also trying to measure, probably we are very few researchers in the world to actually track micromotion. And this is sort of 3 LVDT outputs, and we had tried to measure in LVDT2 gives quite good, quite high response, but LVDT1 is very low response. LVDT3 is in the middle. And we have tried to compare, although there is some deviations, but definitely the trends are sort of similar. Now, we had performed this experiment and published the work in 2010. Published it in 2010, and we had conducted this work under the UK-India project, collaborative project with University of Southampton. But we realized the disadvantages of strain gauge outputs and strain gauge technique as compared to full field data. Okay, so let me list these advantages, which are as follows. Many of these local measurements are required in biomechanical models where irregular geometry and material heterogeneity or inhomogeneity often results in large variation of strain across the structure. Very important is large variation of strain in a particular location. That means there is strain gradient. Okay, if there is a strain gradient, sharp gradient in the strain field, it is unlikely to be captured in discrete experimental measurements like strain gauge. Okay, therefore, a continuous field, full field strain data would be of benefit, such as that predicted, which is similar to those predicted by FE analysis. Now, before we move on to the details of full field measurement, you can see here that a strain gauge being mounted on a sort of a specimen, and it is still 1D, that is one-dimensional measurement. Imagine it's 3D complicated geometry, very complex, and actually you require more comprehensive data, say in a region, and sharp variations in stress strain field. So full field data rich experience is what we are looking for. We are seeking full field data rich experience. So we try to measure and visualize the entire structure's response. And what is response? Response is 3D displacement, displacements and strain gradients. And we would like to measure these things in a complex material and having different complex, complicated geometries. Okay, so you can see here that already there's some figures which there is the representation of full field data. So there's been a lot of work going on parallelly to actually measure full field strain, and digital image correlation is one of the very non-invasive technique. Okay, it is a non-contact technique. Okay, contrary to strain gauge, where you have to fix the strain gauge with a glue and then do all the instrumentation and very, very precisely, then only you will get a very good quality result. The quality of the strain gauge used, the quality of the instrumentation used, the quality of the procedure of the researcher fixing the strain gauge all contributes towards the accuracy of the results. But now we have a technique which is non-contact. However, it is not easy. Okay? So you can see already some representation of biomechanical testing on the left, and you can see on the top that there are, two light sources, white light sources, and you can see here two cameras which are actually measuring sort of strains and displacement in a full field manner. So what is DIC? DIC is a non-contact optical metrology to measure full field surface deformation on practically any material subjected to forces. Okay, so this is an example of our own testing. So on the left there is a pelvic bone, and on the right we have a femur bone. These both are natural, and you can see that here you can see two cameras pointed on this specimen. There are also two cameras pointed on this specimen. But what is striking is these colors, and you see there's a sort of white and there is some black dots called speckle generated on this white paint, which is this white paint is actually applied on the surface of the specimen. Okay, we'll go to the next slide, which explains the working principle. So we have the specimen. You can see already the speckle generated here. We need a light source, a white light source, because it's an optical method. So you have to be very careful with the light source you are using. Sufficient. All are actually reported in a standard manual in this VIC 3D. Okay, I'll list that later. So there is light source, there are cameras. For 3D measurement you need two cameras at least, and then this is connected to a computer, and the computer has some software which analyze this data. So we need two subset of data corresponding to one, say, point or a pixel. One is before deformation, the other is after deformation. And the whole method is based on how they are tracking the movement or displacement of a point before deformation and the same point how it behaves after deformation. Okay, so you have the subset and you have the position of the subset before deformation, and it moves to the area matched with the subset after deformation. So matching the subset before and after deformation is the main principle of the DIC technique. Now we will be correlating subjects, so we will be trying to minimize, we will try to track down which point or pixel is being monitored. Okay, so we will try to match the gray values, similar gray values, that means the same pixel, and try to minimize the error, and then we'll also try to maximize the correlation between the same pixel before and after deformation. Very important component of this whole technique is generation of the speckle pattern, the white dots. Okay, and with experience we have seen there has been several techniques, or sometimes suggested by the manufacturer himself, or sort of researchers who have tried different techniques of applying the speckle pattern, and they try to improve upon the results, because this speckle pattern, generation of the speckle pattern, will actually determine the accuracy of the measurement. Okay, so we actually apply a white paint, very thin layer of white paint, and then we apply the carbon black speckle, very sort of black one, Mars black or carbon black. You can, these are acrylic paints, you can water soluble, and you can sort of prepare it straight away in the laboratory. But the white paint, you can use the spray painting, sort of, you have the handy ones, like the perfumes and body spray. You can spray it, but at a distance. Okay, so if you have a specimen like this, and then the spray, try to spray it from a distance. Okay, so that you don't actually generate very thick layer of paint. It should be a very thin layer of paint, and try to be uniform, as uniform as possible, at least in the area of measurement, the area of interest. Okay, so the displacement of the speckle patterns are recorded by the cameras, and then the VIC 3D correlated solutions. This is the company which is the manufacturer of the software VIC 3D, and they are actually helping us to calculate the strain field in a selected region. So you can see here, I've tried to magnify the strain field, okay, the speckle pattern, speckle pattern on the specimen, and this specimen is actually a lamb femur. Okay, we have been testing a lot on the composite femur, composite pelvis, but there has always been the question that how well will this DIC, what will be sort of the quality of results predicted by DIC when we are measuring on real tissue. Since it was difficult for us to get hold of cadaver samples, we used the sheep bone, and we cleaned the surface, and we had applied this whole technique and measured strain fields in a sheep femur. Okay, it's an ovine femur. We'll come to results later on, but before we move on to the results, just to give you an idea of what is a bad speckle pattern and what is a good speckle pattern. So bad speckle pattern would be repetitive in nature. You need a randomized thing, low contrast, repetitive, and bit anisotropic. That means there is always a pattern. We don't need a pattern, okay? We actually need non-repetitive, isotropic, high contrast speckle pattern to give you the most suitable results or most acceptable results. So these are examples of that. You can write down the source, the Vic 3D 2010 testing guide. Now here are sort of the steps. So we have a 4th generation composite femur from sawbone, and this is a standard geometry of a femur, a viable alternative to cadaveric femurs. Okay, you can see here. And then we actually implant it with a furlong HSC stem of, this was done by Southampton General Hospital for us and made it ready for the testing as a part of the UK-India collaborative project with Southampton University. And you can see how nicely this white paint and subsequently the speckle pattern, high contrast random speckle patterns on the white paint. Remember, I just forgot to mention, the white paint has to be matte finish so that there is no reflection of light. Reflection of light will completely jeopardize your results because it's optical method, okay? And there are two, there's a light source which will be sort of impinging on the specimen, right? So matte paint, matte white paint is very, very important here. So black speckles, and through experience, thanks to the effort of our PhD scholars, we have actually discovered that if you use this toothbrush, dip it into the sort of pot containing the black paint and flick it with the fingers, a very basic kindergarten education, I think, how to paint something, and then we get this. Okay, what is the most desirable result? So this is very low tech, you know, very low tech, very handy. Only you will spoil your tip of your thumb at least for half a day or a full day maybe, then you have to wash your hands properly. But this is the most effective technique of actually getting the most accurate results using this method. Okay, that is, up to now this has been the most effective method. The airbrush, other things, whatever, laser and all these things, doesn't work. Okay, and it has always been the question that why do we get continuously very good results? Even that Nico asked me, what is the secret that you get this quality of agreement between FE predicted and you know, measured strain? I said, there's no secret in the DIC. This is what we use and what we get. Okay. So you can see very clearly how this is generated, and it is all random speckle patterns. So we tested this natural femur and the implanted femur, and this is basically output of the very recently, last week, he has been awarded PhD, the work of Dr. Shobtik Chandra. Now, when we compare and verify the finite element model results, you can see on the right we have the FE measurements, FE predictions, sort of the stress patterns, and on the left we have the actual measurement, and one is for the natural case, the other is for the implanted case. When we actually, this is a data rich technique. So apart from the stress patterns that we get as output, we can also extract discrete values at the points within the region of interest. Okay? So when we actually plot the points with respect to the Fe predicted strain, we are actually getting a plot scatter diagram like that, and as usual this line is the ideal line about which these points are distributed. So here we get a correlation coefficient of 0.926, standard error of the estimate very low, 26 microstrain. We have regression slope, linear regression slope close to 1, not really absolutely 1, but close to 1, and the low percentage error of the B, that is the regression slope. So the intercept also is close to 0. So T statistics, everything when we perform the sort of testing of hypothesis, we are in a position to say that the Fe predicted strain are a valid predictor of the actually measured strains. So more about measurements, you can see also the random speckles pattern on the generated on the pelvic bone. Now we thought the DIC is a new technique, right? But our age-old friend strain gauge is still alive, okay, alive and kicking, okay. So why not try to validate the DIC measurements with the strain gauge, the age-old robust technique, strain gauge measurement. So what we did, we actually erased of the paint by sort of acetone. If you use acetone, you can actually dissolve the paint on the surface. You know, it's a very good solvent, and we actually, you can see some traces of whites on the surface still there, but we actually put strain rosettes, 5 strain rosettes on different locations, just random, and try to measure the strains at these locations and compare it with the DIC measurement. Apart from that, we also try to track the movement of the acetabular component, which is an uncemented component. Okay, it is a cementless component press fitted within the acetabulum, and we try to measure the micromotions along 3 orthogonal directions, 1, 2, 3. Okay, this is a sort of the equivalent finite element model that we generated. Remember, you have to specify exactly, you have to reproduce the testing conditions in this FE model, okay? Otherwise, you will get obviously deviations. It has to be absolutely same. So here we see sort of the comparison, the FE results on the right, intact and implanted, and you can observe straight away that here you see these high strains on in this location, which disappears after implantation. So again, the evidence of strain shielding. Correlation between DIC and FE predicted strains, but most importantly, correlations between the strain rosette and FE predicted strains are also very high. Okay, so we are in a position, you can see how many load cases had been tested, starting from 700 to 1400 for both the samples. And since all these 3, one is the numerical technique, the FE analysis, there is a strain gauge measurement, there is a DIC measurement. So all these 3 form a triangle, but all these 3 are closely related. So we are in a position to say that this FE model is not only a valid predictor of the actually measured strain, but also the DIC measurements are validated by strain gauge measurements. We have also compared the linear displacement sensors, the FE model predicted, and the actual measurements. And you can see very high correlations between these two. Now, this is the ovine bone specimen that we had actually measured. You can see we had also first conducted a DIC experiment, then tried to erase the paint with acetone and then put strain rosettes again to validate the DIC measurements. So at different location, if I go, the femur shaft is here, and if we try to measure along this in this region with change in curvature, how the results are actually affected, because the cameras are pointing from this direction, and the best results you should get is when the direction of the cameras is normal to the area of measurement. Okay, so if you go round as I had done for presenting the results, we have medial location, then we have anterior location, we have anterior lateral locations, and we have lateral locations. So first principle, second principle, and if we do this regression analysis, DIC and strain rosette measurement, we see this. We did not get too many data. This is, I think, about 24 data points, but it is mostly compressive, only few tensile, a cluster of data in the tensile strain regions, but this is the sort of correlation that we get when we compare strain measurement, strain rosette measurement, and DIC measurements. Very high regression slope, very close to 1. Okay, but this might be dictated by the endpoints actually. I would be critical about the result if we had got more measurements, something around say 50 or a little bit more, we would have been more confident about the relationship between these two, but that was not possible because it is very difficult to do this test, and we have a very small timing window, okay, because it's a fresh bone from the butcher. Okay, so we had taken this from the butcher, but you see all these sample preparation and all these method to make it ready for testing takes time, and you cannot leave the specimen out at room temperature for quite some time. Okay, the properties will change, and these will actually have effect on the accuracy of the predicted results. So we have very small time window, taken out of the refrigerator, stored at minus 25, 30 degrees, then defrost, and then put all the strain gauges or DIC paint, speckle pattern, and you have to conduct it in 1 day. And it's a long day, but at the end, it's a satisfying day. So the conclusions are, the results demonstrated a good corroboration or correlation between DIC and established strain gauge technique on ovine femur bone. Data supports the validity of DIC technique to obtain full field strain data on real bone specimen. And the DIC technique can be effectively used for biomechanical analysis of bone and preclinical investigations on implant bone structures, subject to careful surface preparation, which I had already indicated. I would like to acknowledge IIT Kharagpur, University of Southampton, and UK British Council for supporting these studies, and I thank you all for listening. like the MHRD course, so we have some they should take back something solid. Okay, everybody there? Let me have the privilege of introducing Dr. Prasanta Kumar Saha. He's an eminent orthopedic surgeon, currently working as assistant professor in the Department of Orthopaedics, Institute of Postgraduate Medical Education and Research in the city, very age-old hospital, famous SSKM hospital in Kolkata. Okay. He's assistant professor in the Institute of Postgraduate Medical Education and Research, and Dr. Saha specializes in hip joint replacement and arthroscopy. Okay. So we are extremely grateful to have him. He's coming over for a day, leaving aside all this busy with surgery schedule and other appointments. So, and he sort of from the day one I contacted him, he was very enthusiastic about this. So we are extremely grateful that he has kindly agreed to come and deliver a lecture in this sort of course, and I hope it will be very useful for all of you. Dr. Shah.
Good morning. Now, the total hip replacement is called the surgery of the 20th century. মাইকটা লাগান ঠিক আছে। Now, total hip arthroplasty is called as the surgery of the 20th century. It is the most successful operation has ever been done. Now, Sir George Chanley has introduced it, and till now we have a different kinds of implants in there. So many mountains climb and many yet to conquer. About the historical Walter Landau say the present like a note of music is nothing but as it appertains to what is past and what is to come. Now, there are three types of hip arthroplasty. One is called the interpositional arthroplasty, excision hip arthroplasty, and lastly the replacement arthroplasty. Interpositional arthroplasty means we have to put some material in between the hip and acetabulum. Previously, Jacob has first introduced it. He uses as an interpositional material. Later, fasciolata and everything has been introduced, but it fails. Then Smith Peterson, this is the first Smith Peterson who has introduced the cup arthroplasty. This is a stainless steel cup which is put over the femoral head. Acetabulum is not revised. Now this is the picture of an excision arthroplasty. You have to sacrifice the head. It is done in our scenario because we call it a poor metal hip replacement. In cases of infected total hip replacement, where we have no options is there, then we have to remove all the implants, we keep the patient on a skeletal traction for 6 weeks, then we allow the patient weight bearing, and these types of scenario happens, and we call it a excisional arthroplasty. Now the age of hemiarthroplasty begins. We have to cut the head and put the cuff over here. Jude first introduced the implant, and it is made of glass, and it also fails. Then comes the era of endoprosthesis. We are still using the Austin Moore and Thompson's, and they are having very good result. Austin Moore is an uncemented implant, and you have seen that there is some fenestration is there. These are for the bone ingrowth, and Thompson is a cemented implant. So that much of implant is now we have in our hand. That is the White who has introduced first hip resurfacing. You can call it a hip resurfacing. It is a metal on metal articulation, and later we have a thrust plate articulation like this type of arthroplasty. This is case of Muller's metal on metal hip arthroplasty design. We have a Thompson type of cemented implant, and we have a metal cup is there. Then this is a picture of a ring prosthesis. So whatever we have found all over these decades, we have all the implant get failed. Now the cart has been put before the horse, and the artificial joint has been made and used, and now we have to try to how and why it fails. That is remarked by the John Chanley. And the three major contributions of the John Chanley is the low friction torque arthroplasty, introduction of the high density polyethylene, and using the acrylic bone cement to secure the implant fixation to the bone. This is the picture of the first picture of the total hip made by the John Chanley. Now the survivorship, John Chanley, it is published in the Journal of Bone and Joint. There is a 25-year follow-up of the 80% total hip, and revision has been regarded as the end point. And there is a Roblewski also published an article and he said that there is a 77% at 25-year follow-up. So next the concept, why we change the component design? Are we addressing a non-problem? There is a two basic design. One is the composite beam, and another is the taper sleeve. What are the Chanley process we are using? It's a composite beam philosophy. This is a composite beam. The surface is roughened, and pre-coating contributes to perfect bond between the bone and the cement. And this is the taper sleeve pathology. It is a highly polished double joint designed to settle in the cement mantle, has re-engaged in the taper and become progressively more stable. Basically, in the composite beam philosophy, we have found there is a shearing stress between the cement and the implant interface, and also the bone and the cement interface. But in case of taper sleeve pathology, as it subsidence happens, there is a hooping stress occurs, there is a compressive force occurs, which will helps in uniting the cement and help is bondage between the cement and the bone. So debanding at the cement mantle interface presents the initiation of loosening of cemented femoral components. Sleeve between the metal and cement is essential to protect the cement interface. Now we have introduced the triple taper stem. There is a C stem that is available in the Dept. That is the improved loading. There is portion is there is the improved loading and preservation of the bone in the long term. The John Chanley said that his major contribution is the using the bone cement in achieving the fixation. Before the era of John Chanley, you are using the bone cement, but we do not know how to use properly a bone cement. So John Chanley's major contribution is the concept of achieving fixation entirely by means of cement. So cement is a grout, it's not a glue. The surface area of a truncated cone of cement represents much larger surface than the stain, and when loaded, a cemented process transferred the load to the endosteal surface through the hundreds of trabeculae. Now there is a various method of cementing. Modern technique of the cement, cementing is that we have to do the perfect trimming. So we have to compress the cancellous bone. Then we have to do the brushing. So any soft tissue, any blood clots, whatever is there, we have to remove it. They have to done a pulsatile lavage so that all the bloods that is within the marrow cavity that's come, we are using the hypotensive anesthesia. So the pressure will, blood pressure will come. Then we are using the pressurizing instrumentation to for the cementing technique. So the bonding between the trabecule and the cement will be perfect. Now, can we improve the mechanical properties of the cement? Probably not. Whether we are using the high viscosity cement, medium viscosity cement, low viscosity cement, whatever the cement, we are not using, generally we are not improving the mechanical properties. So there is a small changes we have to do. Now the exit type of stem has there is a matted 10% revised at 10 years, and when you have a polished, we have a 2.5% revision of 10 years. So he has a polished stem. Now this is the there is exit and polish. We have a 3M capital stem. There is a 6-year survival of modular flange to stem 8.5%. Now there is a term called as cement disease. It is said that if you are using this, there is a loosening of the bone cement mantle and the there is a progressive loosening. There are some debris. There is a wear and tear much more. But that is not a basically a problem. The problem is this is a particle disease and particle access to the disease. Now cementless fixation, that is why we go for a cementless fixation. The primary objective is that immediate press fit stability and durable biological fixation, and secondly biomechanical compatibility. The problem is that there is a increased thigh pain and there is a straight shielding and there is a osteopenia in the proximal portion of the femur. So distal fixation may produce to the thigh pain. When we introduce an uncemented stem, it will hinges over the anterolateral aspect of the thigh because femur is bow shaped. So if you introduce it, it will automatically touch the anterolateral aspect of the thigh. So when the patient, and in later stage we have a anterolateral thigh pain. So reducing the stiffness of the stem can reduces the thigh pain and reduces the proximal stress production to the osteopenia. So now we have a bioactive coating. The bioactive coating may be tricalcium phosphate and maybe the hydroxyapatite. Now when you're using the bioactive coating, there will be a bone on growth, and it helps in bridge up to 2 millimeter of the gap. And there is a bone on growth, that is implant becomes much more stable. So midterm survival, there is a 100% survival of the femoral component at 10 years, and 99% there is a McLean that there is a 99% survival of HA coated femoral stem at 9 to 12 years. Now a cemented fixation, there is a mechanical interbox, static. It depends on the quality of bone, cement. Consequently, fixation degraded with time. And in case of cementless fixation, we have a biological osseointegration dynamic, and it's a dynamic fixation, bone replaced, and quality of fixation maintained. Now, periprosthetic osteolysis is the leading problem in contemporary Asia. Strategy for the prevention of the osteolysis. So we have to prevent the particle access, we have to prevent and decrease the number of particles, and we have to revisit the cellular response. Because if there is a bioactive particles, the macrophages and other neutrophils, so they are gone, they release the myeloperoxidants and other oxidative stress, and that will destroy the bone. So prevent particle access, we have a cementless implantation, enhance circumferential osteointegration that will prevent the access of the particles in the bone implant interface. Cemented implantation, we should do an effectively cementation to avoid any early bone cement interface lucency. Ritter had demonstrated there is a 38-fold increases of cup loosening associated with what in the early post-operative X-ray demonstrated there is a bone lucency in the zone 1. If we put a cemented cup over here, and the zone of the bone lucency is a non-weight bearing area, that is a zone 1. And if we find there is a gap between the bone cement and there is a radiolucency, that cup will invariably fail within 3 years. Invariably fail. So interference can be sealed with to exclude the wire debris with PTT core Gore-Tex membrane plus butyl cyanoacrylate glue. So this is a physical seal. So we have physically exclude this membrane, exclude the fibrous ingot and enhance osteointegration, and there is a secondary biological seal also. So these are the membrane. So the whatever the wire debris that is produced within the joint, it will not goes into the bone and the implant interface. But what happens? There is also the osteolysis has been found in the long term. Second is the reduce the number of the particles. The great tragedy of the science, the slaying of a beautiful hypothesis by an ugly fact. There is we are using the highly cross-linked polyethylene. There is a decrease in cost, decreased toughness, more vulnerable to abrasive environment. So in an abrasive manner, decrease the fracture and toughness associated with an increase the number of the particles and increase the number in the biologically active range. So hard on hard wearing. So we have a ceramic on ceramic. So ceramic, there is a decrease the surface toughness, wettability, so decrease coefficient of and hard and no scratch sensitive. So aluminum must be of high quality. Tight tolerance must be maintained in the manufacture of the bearing surface, and clearance must be less than 10 micron. Advantage, there is a low coefficient fission, does not degrade with time, minimal wear, there is a 0.25 microns per year, and 4000 less than the metal and polyethylene coupling. And aluminium is an inert material, and the wire particles excite a limited inflammatory response. Disadvantage, it is brittle. Do not mix and match with the femoral heads and more steppers. Avoid scratching and more steppers and clean thoroughly before applying the head, and avoid heavy hammering because it break. So 1970 2000, more than 3000 aluminum and that is and alu couples. There is one fracture head and one fracture socket, and on 1760 femoral heads there is only one fracture in India. So there is now the metal and metal couple. So early metal on metal articulation had a high rate of early loosening and failures. The stainless steel, there is a small clearance, there is a equatorial bearing with increased friction torque. So optimize the clearance by increase the contour but average the equatorial bearing, minimum 30 to 5 mm. Increase the and decrease the angle of convergence. There is an increase in the thickness of fluid film, and there is a fluid film lubrications. So if you decrease the diameter, that will increase the there will be fluid film lubrication. So metal on metal covers wire are 80 times less than the metal on polyethylene. Metal, there is a 25 micron during the first million of cycle and the 4 to 10 micron per millions of cycle. So if you see the polyethylene, metal on metal and ceramic on silicon, wire volume is that in comparison to the number of particles, we have found that the ceramic on ceramic is the best we have now. And then we have the metal on metal, then we have the metal on the poly. Small particles do not excite an inflammatory reaction, but they are biologically active. So to prevent the biological response, basically osteoclasts are the main criminal area. They release all the myeloperoxidase, all the inflammatory mediators, and the interleukin 1 and all this. This will destroy the bones. So we are to prevent the osteoclastic activity. We are using the bisphosphonates that will inhibit the osteoclastic activity and reduce the mechanical loosening of the hip processes. So if there is osteoclastic activity, we have found this at the scenario. The bone is totally destroyed by the cellular response. Now the hip resurface, Smith Peterson, I have said that the first introduced a chromium chloride in 1930. Chandler also used the resurfacing design. Teflon on Teflon, there is a very low friction and there is a very high wear. Resurfacing arthroplasty in 1970s, 80s, these are all the resurfacing. There is a large head, there is a high wire bearings, thin polyethylene, catastrophic failure of that is a cuff. So large metal on metal articulation, we have a McIntyre prosthesis. This is the McIntyre prosthesis. This is the ring prosthesis, and these are all on the metal on metal articulation. So poor early result due to the poor materials, poor tolerance, and the equatorial bearing. But there is an article published in the 20-year survivors with the metal on metal was better than the metal on the ultra high weight polyethylene, the Muller prosthesis. So future trends is that coating have failed due to the harsh environment, which has often led to the separation of the ground. However, if successfully, they could improve wear, reduce frictions, and improve biocompatibility. So these are the newer implant has been gone. There's another surgical technique. We are using the computer navigation surgery implant. Implant we have a proximal loading implant. There's a proximal loading. There's a conservative, no thigh pain, reduced proximal stress protection. These are the hip proxima. This is the original hip implant, and this is only the metaphyseal bearing hip implant. So these are all the pictures of conservative implants we have. Now we have a surgical technique. We have an image guided system, minimal access surgery. These are all the different types of minimal access implants. So conservative, if your preferred hip will outlast the patient, then use it. Preserve bone stock and always think about the revision. Biological solution, bone has the intrinsic capacity to regenerate and structurally and functionally. Articular cartilage, menisci, tendon, ligaments have little or no ability to regenerate, a replica of normal tissue. Now the era of tissue engineering, we create biological tissue using cell, matrix, bioactive factors for the replacement of the diseased tissue and organs. These are all there is a bone morphogenesis, synthetic material, we are using stem cell, these are transforming growth factor, these are all. Now the autologous chondrocyte, it is very effective now in case of osteoarthritis. The chondrocyte implantation within, if you have an injury, we should implant the chondrocyte within 6 months. We have a very good hygiene. There is a evidence of hyaline cartilage formation. So chondrocytes are in the lacuna columnar organization integrated into subchondral bone. These are articular cartilage, highly sophisticated ultrastructure. Next comes the gene therapy. Gene therapy is affected by ex vivo modification with the gene that reintroduced into the body after modification, and in vivo modification which is done in situ. Can these strategies exert structurally modifying effects to counteract the disease process? The delivery of genes that encode the anti-arthritic proteins may present a biological drug delivery system, but safety is the major concern. Gene delivery vectors delivers a stable gene which permits stable and regulated production of therapeutic proteins. Suppression of the activities of the lymphocyte by co-stimulatory molecule against the anti-lymphocyte and suppression of the interleukin. But the major problem is the delivering system. How we deliver the gene to a DNA. Mainly we are using the vectors as a virus. We are using the human papilloma virus and other things. But the problem is that if it is not properly delivered, then the devastating effect of us can change the whole genetic structure of the patient. So strategies for gene therapy in arthritis are gene replacement, substitution of a non-active or defective gene, that is a type 2 collagen mutation or familial osteoarthritis. Gene addition, that is an interleukin receptor antagonist, and gene control, where the expression of a gene is controlled by specific cytokines. So onset of osteoarthritis may be prevented or delayed by transection of articular chondrocyte with HPV proton oncogenes, which will slow the propagation of the chondrocyte cells and replace the sensory cells. In 2000, biological solution will supersede the biomechanical solution. Prevention will reduce the need for surgery, but the THR will still in the ascending for the foreseeable future. This is the just an evolution and how the total hip replacement and how our replacement surgery is going. Now we are going for the gene therapy, we are going for the tissue engineering, because all the implants we are using, they have a lifespan maximum 20 years, 25 years, 30 years, that's all. So now we are going for, all are going for the biological solution. Now start with a hip resurface. I think we have all covered all of this. The concept is that we have to remove the femoral head cartilage, resurface with the metal. It may be a cemented and uncemented, but generally the Birmingham replacement we are using. We have a Birmingham hip replacement, we have a cemented component, and if you have a Birmingham mid-head resection prosthesis, we have an uncemented component. Acetabulum, we are doing a standard thing, we are using the large head. And bearing surface is a metal on metal. That is the major issue. Why you are using the metal on metal or you are using. Indication, we are using it in a relatively young patients with the osteoarthritis. It may be due to the ankylosing spondylitis, rheumatoid arthritis, osteonecrosis, avascular necrosis of the femoral head, or whatever. Mainly young patients, 40 to 50 years, we are using the these types of surface replacements. The concept is that we have, because this any replacement, whatever the replacement we have, maximum lasts for the 30 to 50 years, 20 to 30 years. So if a patient of 20 years or 25 years, you do a replacement surgery, after what you can do. So you must need a good amount of bone stock for the further surgery. So for that reason, we are going for the surface replacement, that we are using only, removing only the head part and the acetabulum part. The rest of the femur is intact. So in the later stages, whether when we do the replacement surgery at the 15 years or 20 years, we have the whole femur intact, we can do easily convert it into a total hip. Now there are some contraindication. The first contraindication is a severe bone loss of the femoral head. Sometimes we found there is a big cyst over the femoral head, or there is a avascular necrosis of the head, the whole material get necrosed, and if we put a cup over that, it will automatically collapse because the bone is have not the adequate, there is adequate bone stock. And relative contraindication is there is osteoporosis, age is more than 65 years, and the body mass index is more than 35 years. So if we do a surface, we are very cautious about the three group of patients. One is the rheumatoid arthritis, because these patients are using disease modifying anti-rheumatoid drugs and the steroids for a long time, and steroid itself causing osteoporosis. And the second is the female patient, where the acetabulum sometimes is very shallow, that we cannot use a proper size of the acetabular cuff. And third is the avian of the femoral head, where you have to identify the how much part of the femoral head get necrosed. That is important. Now advantage, whatever the advantage we have, it is mainly theoretical. There is a bone preservation, there is a preserved femoral bone stock, however makes acetabular preparation more difficult. Improve stress transfer to the proximal femur, so less proximal shieldings and improve proximal bone quality. There is a better kinetics, that is a faster walking speeds, maybe better range of motion, possibly better proprioceptions. Everything is better. So every version of the, easier the version of the femoral bone stock, simply recut and use them, possibly improve longevity. And there is a term called a reduced dislocation rate. And this is a hip replacement has been done and the hip dislocates. So by using a larger head, we will reduce the dislocation. It is not perfectly true. It depends on the soft tissue tension of the hip. If your soft tissue becomes lax, if your posterior aspect of the soft tissue becomes, it will automatically dislocate. So the disadvantage is that poor mobility. If there is a limb length dislocation, we cannot correct it. If you have to adjust the offset, patient with very abnormal unity, better up to conventional TSI, not suitable for elder patient with a poor bone stock. And there is a disadvantage, there is a femoral neck fractures, there is a metal iron problems. That is the metal iron increase in the RB, that is you can find the RBCs in the urine, in the serum. The problem is the metal sensitivity, there is a chances of carcinogenesis, and particularly it is contraindicated of the childbearing age. And fifth is the loosening. Now how we do this is we generally incise the given incision, we have exposed the femoral head. Then with the acetabulum, we have to retract the femoral head, and then these are the acetabulum. We are removing it. We put the cuff. Then we have to put the femoral. Now the femoral head resuscitation place. First is the place the guide wire. So guide wire is through the center of the femoral. We should push the guide wire maximum in a slightly valgus position, more than 5 to 10 degree valgus position. So the less amount of the femoral notching is. So one line is drawn to the mid-lateral plane, second line to the center of the femoral neck. The point is the consection of the beam, and this gives a valgus orientation 5 to 10 degree. Basically, we have all the instrumentation set is there. You just put the instrument over there, and you will have a 5 to 10 degree valgus angulation, and you have to find, will have to go to the center of the femoral head. Placement of the planning of a slight valgus position of guide pin and checking for notching of the femoral neck. An angle in the corner check intraoperatively by the goniometer. There is a guide rod, then the head cutter is used, then the chamfer cut has been done, and ultimately the shape of the head will be like this. Now the head is educated with the pulsatile levers, and then we have to make multiple holes there. This is the trial component. Then the femoral component is introduced, and we have to, in osteonecrosis, if there is a osteonecrosis, we have to remove the bone fragments. Then cement is applied over the defect, and the femoral implant in that place. These are some of the cases. This is the osseous ankylosis. There are ankylosis of the hip joint and replaced with a Birmingham hip. These guys have tuberculosis of the hip. We just replace with the Birmingham. In case of dysplasia of the hip, we just put the design. In post-Perthes disease, we are using this. In case of protrusive acetabolic coxa vera, we are using Birmingham hip. In case of acetabular fracture, avascular necrosis of the femoral head. So the complication is the femoral neck fracture. This is the most common complication. It is early in the learning curve, early in the process of life. There are risk factors. If there is inflammatory arthritis, if the patient is a female, there is a large head net set. If the varus position of the femoral neck, the impingement of the, these are all causing the increase of the fracture risk. If there is a femoral neck fracture, it is very easy. This is we just convert it into a total hip. Just we remove the component, we put the stem is there, and we convert it into a total hip. So there is a early losing. There is a due to the poor manufacturing, the decreased clearance, inadequate polar bearing. Now the modern technique has a small surface expertise, improved fluid film regulation, polar bearing with small clearance, very low iron and little particle production. So these are the oversized heads, and you find there is a notching of the femoral head over the femoral head. There is a varus position of the component. This all leads to a fracture. There is a AVN. We are doing the bone scan, and we find there is an increase in the radio uptake over the left femoral head. Open acetabulum. There is theories to cause sparing and increase metal wire, and there is a we have to reaming the medial wire much more, so that there is a destruction of the medial one, and we have seen there is a illusion is broken down by the cuff. So the Austral GI registry of 2000. What is the current position of the replacement? Austral registry, they have done the by 2000 they have done the 13,300. Best outcome, male less than 65 with osteoarthritis, able to get more than 50 mm head size, and there is a revision by 9 years 3.9%. And cumulative disease, যদি আমরা revision rates if you see that there is a 7.2% in the osteoarthritis case in 9 year. Birmingham division is 6.2% in the 9 year. Reasons for reasoning, mainly the fracture, there is 36%, loosening 33%, and mental sensitivity 7%. And these are all the registered processes. The revision is less than by, that is most important, the revision by age 7 years. We have found there is a age less than 55 years, there are 5.6% revision, and if more than 65 years, so in older age, we should not do this. So revision by the head size, if we find out that if the head size is less than 44 millimeter, there are 13.8% revision rate, and if the head size is more than 55 millimeter, there is only 2.2%. So we are in hip resurface, we are using the large head. So in case of female patient where the acetabulum is very shallow, we are not, it is not preferred to do the surface replacement in the female, that patient. So is there a role of surfacing? Yes, when a stem cannot be placed, if there is a proximal femoral deformity, the femur is bended, there is a osteotomy has been done in the femur previously, so we are not able to put a straight stem there. So in that cases, there is a role of the surface. And how the larger role of the surface? Probably a small role, because the disadvantage also outweighs the advantage. Long-term follow-up we need. There is also need mass series between the apparently normal. Is the functional surface better than the stems or high level activities? This is all about our surfaces. The main problem of the surface is the neck fracture replacement. If we put the cup in a varus position, or if there is a notching of the femoral head, when the patient weight bears, it will automatically bend. Or if it is excessive valgus position, it will automatically bend, and there is a stress over the femoral neck and it will get fracture. And second is the metal on metal issue. And Dept has a artificial surface replacement. They call all this replacement surgery because there is a high amount of chromium cobalt has been found in the female patient in the childbearing age. So they replace all their artificial surface replacement with the total hip now. Now the current issue is the short stem hip arthroplasty. This is the new concept. This is originally long stem. If you put a long stem, we have to cut the gluteus minimus and part of the gluteus medius muscles. But if we have a using a short stem, both the gluteus medius and gluteus minimus muscle will be protected. So bone stock and soft tissue preservation, the getatongan and subtogan at the time of implantation of the future revision. So decreased shed shielding causing metaphyseal bone resorption and diaphyseal cortical hypertrophy. State concentration at the tip of distal fixation traditional component causes thigh pain. With the short stem, that is eliminated. They transfer load to the metaphysis from superior to inferior direction in a physiological manner if you are using the short stem hip prosthesis. Wide range of indication, all types of bone stock with normal femoral morphology are acceptable. Revision surgery becomes easier because minimal invasive approach, less soft tissue damage, and the intact bone stocks below the lesser trochanter. Now the classification. Now classification, we have classified the stem as a type 1, type 2, type 3. Type 1 is a surface replacement, type 2 is a mid-head resection, and type 3 is the short stem prosthesis. And type 3 is the column prosthesis, and type 3A is a column prosthesis, or it may be a partial column prosthesis, and type 3 is a trochanteric prosthesis, that is a trochanteric sparing and trochanteric hammering. This is a type 3A stem, that is a CFP stem, and this is a type 3B, that is a trochanteric sparing and trochanteric hammering stem. This is the follow-up. And all the follow-up we have taken below the 5 years, and below the 5 years, the follow-up is there is a 100% some cases, and some cases 96%, some cases 98% survival rate. But the maximum follow-up is below 5 years. This is a picture of a hip proxima. This is a patient at the follow-up in the 2 years, the implant is very stable. So the conclusion is the various short stems have been introduced with different implant concept of femoral fixation and implant design. There is a lack of proper classification for short hip stems with clear and accept definition for implant length and extent of bone preservation and metaphyseal and diaphyseal. Clinical data collected from a large patient cohort showed survivorship comparable to traditional stem within the 5-year survival period. So this is the all about the new implant we have. Just I have been told that you have been to say about the revision hip arthroplasty. So why we revise the hip? The pain is the major indication for the total hip arthroplasty, revision hip arthroplasty. Now, why there is a pain? It may be a failure of fixation, it may be a failure of the implant, it may be an infection, it may be a periprosthetic fracture, it may be due to the dislocation and technical. The contraindication, if there is a painless loss of motion, there is no need for revision. If we do the revision surgery for the loss of motion, we again there will be a further loss of motions. If there is a painless limb lengthening, there is no need for revision. And there is the preoperative planning. We need a high quality of the radiograph of the pelvis and the entire femur. Lateral femur view is the very important because to know the bow of the femur. Sometimes the cup is dislocated within the pelvis. In that scenario, we need a pylography and the vascular studies, whether the cup is attached with any vessels or the cup is attached with the bladder. And if we directly take out the cup, it will injure it, and there will be torrential hemorrhagic bleeding, and patient will die on the table. And we need a CT scan for the acetabular, especially for the acetabular deficiency. Now, what are the approach for the revision arthroplasty? We have a trochanteric osteotomy, we have a trochanteric slide osteotomy, and we are using the extended trochanteric osteotomy. Now, we all are using the extended trochanteric osteotomy. Now, the first stage is the removal of the implant. So, first we are discussing about the removal of the cemented implant. The first thing is that when we do a revision surgery, it is practically difficult to identify the structures. We have to identify first the sciatic nerve. But if our sciatic nerve is cut during the our surgical procedure, then there is no need to do that revision surgery. So we have to identify the sciatic nerve, we have to retract it. Then we have found there is very difficult to find all the rotators, gluteus medius, very difficult to identify. There is always single structure. The most important during the removal of the implant, we have to clear all the soft tissue around the tip of the bracket. We use a diathermy, that is electrocautery, and we remove all the soft tissue to the around the greater trochanter. Then, if there is an overhanging of the greater trochanter, sometimes there is osteoarthritis, there is an overhanging of the greater trochanter, and sometimes the bone cement is attached toward that part of there. So we have to remove that part of the greater trochanter, or if there is a bone cement is there, we have to remove it. Otherwise, if you try to backhammer it, it will split the greater trochanter. Now there is the extraction. If the stem is, maximum cases we have found that the stem is very loose. We just hold the stem, we pull it and it come out. But there is a different extraction. There is a extraction which is attached to the stem, we can remove it. Sometimes there is a hook is there, we can remove it. Now there is a combination of flexion stone, microsagittal or small bar. Cement removal. We have to remove the cement. For the cement, after the implant has been removed, we have to remove the cement. For the cement, we can do a extended trochanteric osteotomy, or that we have to remove the trochanter from here to here, and then we have to remove the cement by curette, or using a bar, using a bar, or you use an arthroscope. That is a knee arthroscopy. We put that arthroscope through the canal, and we see where the cement is there, and we have to remove it. There are several type of flexible osteotomies there. We go through the bone and cement interface. We just break the bone and cement interface, and we have to remove it forceps. So there is a cement removal kit is available. There is a flexible osteotomes, reverse. Now, when you remove the cement, first we have to break the cement radially. We have to have a thin osteotome. We have to break the cement radially. Then we go to the bone and cement interface. Then we have to remove that cement. These are all the instruments of the removal instruments. Lastly, after removal of the cement, there is a cement plug is there distally. That is very important. We have to remove that side. For the removal of the cement plug, we drill that cement plug with a 3.5 or 4.2 drill bit. Then we have a long screw or long tap. Then we have to squeeze it and we reverse hammer it, and it will come out. But very careful to avoid inadvertent perforation and fracture during the removal of the cement. Now the removal of the femoral implant, uncemented. If it is due to the infection, it is very difficult to remove that because there is a osteointegration is there. If you try to hammer it very hardly, then all the bones and everything come out. So you will not have any bone for the further revision. So consider the component design, whether it's a fully coated stem or it is a extensively, it's a fully coated stem or it's a proximally coated stem. Removal of the proximal is very easy because we have to disintegrate the bone and implant and the bone surface. Then we have reverse hammer. Now the breakdown of the osteointegration. We can break down the osteointegration by flexible osteotomes. We can use a microsagittal saw, or we can use a bar. But bar use is very, or we can use, even we can use an extended trochanteric osteotomy. This is the picture where we have to remove the trochanter with a part of the shaft. Then we use a giggly saw which goes around around the neck and then go around the shaft, and we will remove the implant. Now there is a extraction device. There is a company specific hook under neck. There is all of the extraction devices. Now there is a how we remove a proximally coated stem. That is this proximally coating is likely there is a disrupt the area of bone growth with a specialized thin osteotome. Alternatively, we can use a high sweet bar and extract the step after the disruption of the bone ingrowth. Now there after the extraction of fully porous coated stem, that is very difficult because the greatest ingrowth occurs in the distal part. So first we have to disrupt the bony ingrowth proximally with a osteotome. Then we have a make and window over here with a small bar. Then we have a transect the procedure as a carbide tip metal cutting bar. Then we remove the proximal part. And the distal part is using by a refined machine. We are using remove the distal part. If there is a broken stem or the stem is broken, then how can we remove it? We have a instrument just like it will go through the broken part, and we just reverse summary it, and the implant will come out. Now second is the acetabulum removal. Leave the femoral component in situ. Indication if the femur is not lodged, then we have to remove. There is no need of removal of the femoral implant. Technique can remove here. Now general prescription is that if the cup is loose, then it easily come out. There otherwise we use a carved osteotome. We go between the cement and the implant interface. We just slowly hammering it. Then we have a special type of removing instrument. We just put it here, and then we just take it out. If it's an uncemented, maybe just changing the linear if the leaving the cup, or may need to remove the well fixed cup, or may be removing the loose cup. So linear component specific, there is a removal instrument that we have put over the linear and just take it out. There is a simpler lever out the linear with an osteotome, or there is a very useful method that we have to drill it with a 4.5 drill bit. Then we have to introduce a 6.5 mm screw, and that and it will automatically come out. So metal shell, there is a carved osteotomes, Riggs bone, and we have a IPGMER explant removal system. This is a IPGMER explant removal system. This is the cuff. These are the small blade. This is the large blade, and this blade goes between the bone and the shell interface. And after breaking down all the bony integration, we have to remove the. There's a beautiful instrument. If there is an intrapelvic acetabulum or if there is an intrapelvic cement, issue can be life-threatening if we just pulled out from the standard approach. So workup, preoperative contrast study, general surgeon or vascular surgeon may be needed. If there is no aneurysm, we just lateral ilioinguinal approach, elevate the iliacus muscles and remove under direct visions. Or if there is a false perfusion, we need a vascular surgeon, we go for a Rutherford Morrison approach. So the revision is So revision is very complex. It is a very lengthy procedure, and it's also challenging. We need an A team for doing a revision surgery. After the removal of the human, we have to revise with a acetabulum and we have to revise the femur. Now, what are the options we have? First, we classify the deficit, bony deficit. After removal, there is some kind of bony. We have a AOS classification, we have a Paprosky classification, we have the gross classification. But all over the world, all are using the Paprosky classification. That is very easy. So the principle of acetabular reconstruction, we have to restore the center of the rotation, restore the central acetabular integrity. There is a component containment, and we have to secure it firmly. So the preoperative plan, known the components in situ, quality and grade of bone defects, bioper of intrapelvic cement or cup, then we need an angiogram. The basic line guidelines is if the more than 50% of the host bone content, we use a press fit uncemented cup, and the rest of the defect can be augmented with screw. And if there is a less than 50% of the host bone, we use a metal augment in elderly to reconstruct the defect. We can use an allograft augment in young to reconstruct the defect. We can use a press fit cup, or otherwise you can use a cage. So this is the classification. The type 1. Type 1, there is a no migration of the component, there is a no bone loss, and there is an intact supportive ring. This is a type 1 deficiency. We have a there is a no migration of the component. The intact acetabular rim is that the ilioischial line and iliopectoral line both are intact. So there is a no breakage of the column. There is a type 2. There is a type 2. There is a hemisphere is distorted, and there is a superior migration of the femoral head. And the migration may be anteriorly, maybe laterally, maybe medially, maybe anteriorly. And in these cases we have a hemisphere is distorted less than 2 centimeters superior medial and lateral migration, and we have an intact supportive column. That is important. So type 2, there A is a superior medial migration, type 2B is a superior lateral migration, and type 2C there is only medial migration. So according to the type 1, type 2A and type 2B, we have found there is a rim is intact. Oh, there is a mild superior migration, and there is a less than 30% of the superior rim is missing. So we need, what are the options we have? We have an uncemented jumbo footing cuff. There are cuff size larger sizes. That is, the cuff is 54, 56, 58 sizes. So more than 50, the indication is if there is a more than 50% bone is available for ingrowth, and more than 2/3 of the rim is intact. So mainly there is a deficit is over here. There is a superior portion, and if the 2/3 of the rim is intact and more than 4, we go for just uncemented jumbo fit cuff. So what is the technique? The implant is positioned in the usual position. We rim anteriorly because most of the cases the posterior bone is destroyed. Some uncovering the superiorly is allowed. If there is a usually the augment with screw is generally not required, and postoperatively patient is not bearing. This is the case of type 1 12 to type 1 defect, and we have to reduce with a jumbo cuff. There is a 12 to 15, and the result is that is a 12 to 15 year survival, 80 to 96%. Second is that we have to impact bone graft, we have to use a mesh, and we have to use a cemented cuff. There is a this is a type 2A, that is a defect. We have to impact the bone graft, then you put the mesh over here. Mesh is fixed with multiple screws, and then we have a cemented cup out there. And type 2C is a medial wall deficiency. So the option is that particulate the graft medially, that is a type C deficiency. We have given the graft is over there, and we put a jumbo cup here. Then impaction bone, is we can, this is a type 2C deficiency. We have seen there is a medial wall defect because the ischial line has broken down. So we put a graft mesh is there. Mesh is fixed with multiple screws. Then we put a bone graft. Then we put a cemented cup. And we can only use the cement if the patient is very old. This is there is a medial defect and of the cemented cup, and we have done the totally preparation. There is a cement process. So there is a segmental medial. If there is a segmental medial wall deficiency, what are the options we have? We have an allograft, anteprotrusion case. Then we have a cemented cup. So here we find there is a the picture is very bad. There is a allograft is there, and this is an anteprotrusion case which is fixed with multiple screw, and then we have done a cemented cup. Now there is a type 3. In the type 3, there is a superior migration is more than 2 centimeter, and there is associated with there is a ischial bone deficiency, ischial and medial osteolysis. So this is a type 3 deficiency. Now the type 3A, there is a collar line is intact. That means the posterior column is intact. There are 30 to 60% of the components supported by the bone gap, and the bone loss is mainly from the 10 o'clock to 2 o'clock positions. Type 3A, there is a more than 50% of the more than host want to reconstruct the defect but do not need a cage. So what are the options? We have an uncemented rim-fitted cup. Then we have a structural bone gap and screws. The indication is that defect is the superolateral of them less than 50% to support the cup. More than 50% of the host bone corner. Allograft will not go on to the uncemented, and allograft to reconstruct the defect. So this is the picture of allograft. There is a defect. We have to put that allograft is there, fixes with the screw. Then we rim it, make it the acetabulum, and then put an uncemented cup. Then the impaction bone graft plus minus mesh plus cement, when we can use a cemented cup. It is required if a convert an uncontained defect into a contained defect. We can use a titanium mesh fixed with screws, then the acetabular rim and the medial wall mesh striker. So impact mortalized bone graft, TAMs over there. We have do the reverse rimming, and then we insert the processes. This is the case where the we do a revision. We put the graft is over there, then we reverse rimming it. We put the meshes there to secure the graft with multiple screws. Then we do a cemented processes there. This is another cases. We are not using the mesh. We are just putting the graft over there and do a cemented processes. So results of this, that the 85% survival in the 12-year survival, and 80% of 15-year survival. So important point is that rigorous technology is important. Fresh frozen allograft does this prefer better than irradiated bone graft. Now we have a trabecular metal components. These are the new metal we have. Now there is the interconnecting porous metal. There is 80% porous and allows 2 to 3 times bone ingrowth. And it's a less shift, so improved remodeling on bone underneath. So high cancellous bone coefficient, excellent initial stability, may need less traditional 50% contact and may not need screws. Then we have a bilobed acetabular components. If there is a deficit, so indication if there is a superlateral deficiency, there is a DDH problem, there is there, but very difficult to get the version. So this is a bilobe cut. There is a deficiency. We put the cup and we fix it with multiple screws. So type 3B, there is a less than 50% image intact and less than 40%. So we must reconstruct for stability. Unable to use an uncemented processes, usually bone graft to reconstruct, and we need cage for the stabilities. So structural allograft with cage. So when inadequate bone stocks is there, cannot is there. That this is a structural allograft is there. We put antiport to show cage is there. Then we have done a cemented implant, and we have found there is a 10 to 15-year survival in 70% cases. Then is a custom-made triphalange for which we need a city model, and by which we have made a triphalange cups, and that will this is a custom-made sorry. Now they have an impaction bone graft plus mesh plus cage plus uncemented cup. So this is the total disruption of the ilo-ischial lines and ilo-press. So there is a total medial wall deficiency. The cup goes upward. That's a superior deficiency. So in these cases, we put the cuff. Then we fix it with a mesh with multiple cages, multiple meshes. Then we put an antiport to show cage. Then we cemented the implant. So implication massive delay, result 90%, only 4.5 years survival rate. If there is a pelvic discontinuity, or there is a pelvis fracture is there basically due to the trauma or any other thing, or due to the infection, we find there is both the iliopectineal and ilo-ischial line is broken down. So we have to plate and bone graft the posterior column. So plate plus we can do a case reconstruction. Then there is a three is a cup case reconstruction. This is the cup case reconstruction for the acetabular deficiency. So conclusion is the results are very surgeon dependent. Many centers have developed a technique that works for them. Result depends on multiple factors, that is patient functional demands, patient case, osteoporosis and everything. Do you have any question about the femoral acetabular revision? Aste? Huh? For the femoral revision, what are the type of implant we have? We have a long stem cemented revision femoral stems. We are using the modern cemented. We have to remove the advantage, use in all cases, good with elderly fragile bone, and we can use the antibiotic with it. Indication, we have a use in the Pappro scale. Later we will describe what are the Pappro scale classification 1 to 4, very versatile. Technique is the complete removal and debridement of the necrocortex and modern cemented technique. And we have found that is at 98% 10-year survival rate. There's a problem is that if I do an extended trochanteric osteotomy, then if you do a long stem cemented implant, the cement will goes in between the fracture site of the extended trochanteric osteotomy. So there is a problem of union. Then externally porous coated diaphyseal fitting uncemented stem that are mainly indicated in type 1, type 2 and type 3. Result is 90 to 95% 10-year survival. Problem is there is a fracture, there is a stress shielding with additional proximal bone loss. Then you have a modular diaphyseal fitting proximal filling uncemented stem. Its design is a press fit metaphyseal segment slotted under diaphyseal initial stability to distal. Indication is that type 1 to 3B, and there's a nil division at 5 years, and 7% is radially loose. So these are all about the uncemented implant, modular uncemented implant. We have a calcar product, we have a fluted distal part, and we can changes the version and the neck length. So another is the impaction bone grafting that we can do that, remove the implant. We have impacted the bone graft and we have cemented implant. Now start with the classification. There is a type 1 classification. There is a minimal metaphyseal cancellous bone loss, and we have an intact diaphysis. So there is a minimal bone loss, intact diaphysis. This is a type 1 femoral deficiency. Option, simple revision, can use a standard or any revision set. It may be an uncemented standard length proximal fit and need appropriate initial stability. This is the case. It is the infected total hip replacement done previously. Then we use the antibiotic impregnated spacer. After that, we remove that spacer after 6 weeks, and we just do a uncemented total hip. We can do a cemented standard length stem. That is a must. Remove the neocortex, need good cement integration, and there is a 90.5% in 19 years survival. This is a bone cement. We just remove that implant, and we have done again. Cementing has been done. Cement into old mantle. There's a clean and dried up mantle, critical thin layer of blood, 85% reduction shear strength, and there is a 19 cases. There is a no loosening at 5-year follow-up. That we have removed that implant, and we again cemented, doing a cemented total hip replacement. Now start with the papyroscope type 2. There is an extensive loss of the metaphyseal cancellous bone, but there is an intact diaphysis. I have found that there is a extensively metaphyseal bone loss, but the diaphysis is intact. So option is externally porous coated diaphyseally sitting implant. Papyroscope 90% osteo-integrated. We have done this. Then you have long stem cemented revisions. Then modular diaphyseal sitting, metaphyseal sitting, uncemented person, or we can do a impaction bone grafting and then do a cemented implant. Now papyroscope type 3A, the metaphysis is severely damaged and non-supportive, and more than 4 cm of intact diaphyseal bone available for distal fixation. The metaphysis, this is the case where you find there is a total metaphyseal bone loss, and the distal 4 cm bone is available for the distal fixation of the stem. So externally porous coated diaphyseal fitting implant we can have, and that the papyroscope we have done, that is a 91%. That is a, among the 22 cases, 20 there is osteo-integrated. There is a long stem cemented revision stem. We can do this. Then modular uncemented, and we can also do a impaction bone grafting. Now type 3A, modular stem, there is a case where we can do a modular long stem. Now femoral deficiency type 3B, the metaphysis is severely damaged and non-supportive, with less than 4 cm bone is available for distal fixation. There is a metaphysis severely damaged and less than 4 cm bone is available for the distal fixation. So what is the options? Option is extensively coated diaphyseal fitting stem. Papyroscope has done 8 cases, among the 4 cases failed, need more than 4 cm for this work. Or we can do a long step cemented revision stem, modular uncemented stem with flutes and rotational stability, or we do a impaction bone grafting, etc. This is the case of type 3B. This is an infected case. We are putting a antibiotic spacer. Later, after 6 weeks, the spacer has been removed, and we're doing a uncemented modular implant. This is the type 3B cases. There is a severe bone loss, and the femur, and there is a loosening of the processes. And we have done, there is a cemented, uncemented modular implant with osteotomy warrior to correct the bowing of the finger, and with fixation with multiple wire cables. Now the type 4 one, here is in conjunction with the metaphyseal diaphyseal, in conjunction with the wide and femoral canal. The isthmus is totally non-supportive. So this is a type 4 deficiency. We have nothing to here to fix it. So we have a long stem cemented revision stem, or we have to do a revision bone. So what we have? We have a segmental bone defect. So for this we have a we can do a cortical. We have to bypass by any cortical layer by 2 cortical down to reduce the fracture, or we can have a cortical start on leg out. Or we have a extensive proximal bone loss. We have a calcaneus sparing indication proximal segment even less than 3 cm. This is the case of proximal segmental prosthesis. There is a napkining or calcar graft allograft. Circumferential proximal defects less than 6 cm. Results are photoresidential. Then a proximal femoral replacement, and we have a tumor process. Result is very disappointing. However, design is improving now. Now this is a case where extends we have done there is infection and there is extensive bone loss, and we have replaced with the proximal femur replacement processes. But the results are very poor. There is a bulk structural proximal femoral indication if the defect is more than 3 cm. There is a defect is more than 3 cm. The proximal allograft with process has been done, and it has a very good result. So these are the algorithm that how we manage according to the papyroscope classification the proximal femoral deficiency after revision. Now, there are several complications of the total hip replacement. There may be a neural injury, there is heterotropic ossification, and everything. But the most important is the three. There is a dislocation, infection of the total hip, and there is a periprosthetic fracture. Now, first we deal with the dislocation of the total hip. The point must be made that an occasional post-operative dislocation is no disgrace. Patient can sometimes be quite irresponsible and unreasonable during this period. It is the only in recurrent subluxation or dislocation that the surgeon might have hold himself responsible. That's said by the surgeon, the father of the total hip surgery. So total hip dislocation is a painful complication in which the femoral bud is comes out and its place is a cup component and moves outside the total hip. So this is the dislocated hip. We have a void cup is there. So the mechanism of dislocation, there is an impingement of the neck of the head against the rim of the cuff. So we have found that the neck impinge over the cuff at 90 degree, and if we go beyond 90 degree, there is a tendency to dislocate. And if we have a weak capsule, the definite dislocation will happen. So the mechanism is so other causes is the weak soft tissue, weak abductors, weak capsule. And second is the wrong position of the component. If the femoral component is properly not anteverted, femur is anteverted and the SW is not properly anteverted, if it is retroverted, there is a high chance of dislocation. So stability of the restoration of the balance in the soft tissue and on the total hip, good position of the component, the size of the head, large head makes the total hip joint more stable. So good position of cuff in the stable hip. And if we have a cuff is like there, then at 90 degree, it will impinge over hip and it will dislocate. Now flexion is more than 90 degree if you have a large head, and if we have seen that amount of flexion is there, and if you have a small head, then you have less than 90 degree flexion. So how does it happen? This is a very important report. If a surgeon performs 6 THRs annually, he experiences 4.2% dislocation, and if a surgeon performs 50 THR annually, he experiences 1.5% dislocation. So it is totally a surgeon's dependent. So factor increasing the risk of dislocation, there are several factors. We can have all these. There's the advancing age, neurological problems, weak abductors, everything, and non-competence of the patients. So the important surgical is the wrong position of the total hip. That is the most common cause of the dislocation. What we have, we have to put the acetabulum. Generally, there is no problem to have the femoral problem. We can put the femur in proper anteversion. The problem is with put the acetabular cuff. Acetabular is anteverted. It is anteverted 10 to 15 degree. You put the cuff in a 10 to 15 degree anteversion. Now in different diseases, it is very difficult to put the cuff in anteversion. If you have an ankylosis of the hip, so to cut the neck, we have all the other bone is there. So you do not know where is the center of rotation and how you put the cuff. And generally, we have a very structure called a transverse acetabular ligament that will lead us to put the cuff perfectly. But in case of ankylosing hip and in case of severe infection, and if a surgeon done arthrosis, they will deliberately cut that transverse acetabular ligament. So it is very difficult to know. Now, if you have a patient have a abduction deformity of the hip, both the limb are abducted position. Generally, what we do, we put the patient in dead lateral positions. We retract the femur anteriorly. If we think that we retract the femur anteriorly, and another retractor was there posteriorly, and we put a Steinman pair for the retraction of the superior. Now, if the femur is there in this way, we put the femur in 45 degree, then we put in this way 10 to 15 degree anteversion. Now, if the patient has a opposite limb abduction deformity, so when you put the patient in lateral position, the cuff will be like this. So in this position, if we put a 45 degree inclination and the cuff will be more horizontal. Similarly, if the patient will have an adduction deformity on the opposite half, in put the cuff in, the cuff will be more vertical positions. So that is why the position transverse acetabular ligament is the most prominent structure, and if it is destroyed, then we have to use the C-arm, that is for the proper position of the cuff. Second is the failure of the restore the leg length, limb length discrepancy. We have to do a proper preoperative planning and templating to know how much limb length discrepancy is there and how much we have to correct. Generally, maximum 4 cm has been corrected. If you overlengthen the limb by 2.5 cm, there is definitely a foot drop due to the common peroneal nerve palsy. And if you increase it by 4 cm, there will be sciatic nerve palsy. So you have a maximum 4 cm length acceptable. Then failure to preserve the strength in the abductor of the muscles. That is very important. Generally, all the operations we are doing here, Generally, we do not cut the abductors, but in some cases, we do a trochanteric osteotomy. We do a sliding trochanteric osteotomy. Then we have to fix the trochanter very well. Other, if the trochanter goes into a non-union, there will be abductor weakness. Second is if there is a neck length is become short, then the abductor length will go and the abductor weakness will be there. So implant risk factors, if you use a 22 millimeter head, there is a high chance of dislocation. And if we use a more than 20 millimeter, there is a 36, 38 millimeter of the head, there is less chance of dislocation. So how to reduce the dislocation? There is acetabulum 11 to 28 degree anteversion, 40 degree inclination, and femoral stems 10 degree anteversion. Good soft tissue management and the patient training. Patient has been asked not to do the squatting cross-leg sitting. That will dislocate the hip. Then the soft tissue management, we have to repair the capsule and the short external rotation, not to damage the abductor system. So the patient training, we use a abduction pillow. This is a abduction pillow. We put the non-compliance patient, we have to do a spica cuts, and we have to rehabilitate the patient how to start sitting, standing from the sitting, restoration not to sleep prone position. Symptoms and signs that totally is very painful condition, dislocation. Feels very popping up the something coming out from the head. Treatment of the first dislocation. If the patient has a first joint, this is a conservative. Reduce the patient, we give a longitudinal traction, and post-operation in the abduction orthosis, a spica cast for 4 weeks. This is the 8-year-old development. The hip is dislocated. If the dislocation was the second times, we manage the patient with spica cast. So the repeated dislocation, the first dislocation that occurred during the first 3 post-operative days was treated accordingly, has a low risk of about 20 to 30% in the next years. But after another second dislocation, the risk that the total hip will continue to dislocate and increases substantially according to the statistics. You have 50% of the patients who had 2 dislocations continue to dislocate and that totally repeatedly. So examination after the second and further comprehensive X-ray, CT scan, fluoroscopy under guidance. So operation to improve the stability, revision of the faulty position of the component, operation to relieve the slackness of the soft tissue around the total hip, that is a soft tissue advancement, changes the length of the neck, revision, constant cuffs, or a bipolar hip prosthesis. So if you have this is a short neck, you have slack capsules. What can you do? You increase the neck length. So tighten up the soft tissue will get tightened. Then abductor muscle level of shortness. We have to advance of the abdominal delivery and fix it. And if we have a small one, we have been small one 22 millimeter, we have to replace it with 36 millimeter of it. If we unstable a normal cuff, then we can use a constant cuff. So there is a ring locking and there is no. If the ball subluxates, we can have a locking ring that keep the ball in place. Cuff articulates directly with the sockets. And then you have a bipolar process. All will help in treatment. So dislocation of the polyethylene, dislodgement of the polyethylene lining is an increasingly common complication following total hip arthroplasty. So what are the symptoms? Painful limb and shortening of the limb. Treatment operation of the dislodged linear is necessary. The surgery should be done as much as possible. Oh, slide. Now the second most common complication of the total hip is the periprosthetic fracture of the femur. What is we have to understand the incidence. We have to understand that open reduction in terms of proximal Vancouver B fracture has a high failure rate. The distal B1s and the C fractures with a single lateral plate have a high failure rates, and we have common. Now about the Swedish registry. What are the reasons for reasoning? We have aseptic lesioning, dislocation, and periprosthetic fracture. And incidence has increased since 2000, and femur still more common than the acetabulum. Now the Mayo Clinic is that the post-operatic fracture, they have said that 1.1% in the 23,000 patient and 4% in the revision cases of THR. The intraoperative fracture 3% in the 20,000 patient and 5.4% in the 3,000 patient of THs. Now what are the treatment? There the Bears have published a letter. If we treat the periprosthetic fracture non-operatively, there is a 40% deformity, 11% non-union. If we do a cemented revision, we have a 30% non-union, 15% new fracture. If I do only the open reduction and internal flexion with the plate and screw, there is a 13% fixation failure and 30% new fracture. And if we go for a cementless revision, we have a 7% new fracture and 7% shortening. So the conclusion is that incidence is increasing, particularly acute fractures according to the Swiss registry, and fracture of the total joint continues to increase, and the lifespan is increasing. So all these contributes to the increasing in the incidence. So now the out of our past effort to manage this fracture is inconsistent. So first thing is the classify fracture. PK classification scheme that defines the treatment. Femoral side, we are using the Vancouver classification A, B, C. In the acetabulum, it is very simple. It is outside rim fracture or inside. If the fracture goes through the acetabulum, the cup will be inherently cup will be loose. We have to revise it. And if the fracture goes outside the acetabulum, then if we find out whether the cup is stable or not. If the cup is stable, there is no need for revision. So things to do: define the fracture location, define fracture pattern, define the host, that is the bone quality, activity level, age, etc., and define prosthetic physician, and define the time since the joint implantation. So in Vancouver classification, there are some deficiency. Vancouver classification does not consider the time. So now we have a timing added time classification. So we have an early fracture that is often treated differently than the late fracture. So early fracture, intraoperative within the 6 weeks. If the fracture around the greater trochanter, that is a type A fracture, that is and lesser trochanter, that is a type A, if it is displaced, we need a fixation if the stem is okay. And in the lesser trochanter fracture, generally stem is loose, we have to revise it. Almost all the B fracture stem is loose, and almost all C fracture treated as a late fracture. What are the risk factors? That the cementless, the tapered stem, minimal rapid mobilization, and the osteoporosis. If the fracture is more than 6 weeks, usually need grafting and augmentation. And if it is on over the lesser trochanter, usually fixed with encircle as well. And most of the type of the most B fracture needs revision, and type C fracture most will need fixation. And here the risk factor is the osteolysis, osteoporosis, and incomplete cement mantles. So this is a Vancouver type A. There is a fracture of the greater trochanter or fracture of the lesser trochanter. So what we need to fix? We need a 8-10 gauge wire cables. We need a wire passer. We need trochanteric plate, pointed reduction forceps, and other reduction clamp. This is a Vancouver deficiency. There is a greater trochanter early fracture related to the insertion repair with a retention. We use a trochanteric fixation plate. Post-operative partially weight bearing, no active abduction and abduction brace. In the Vancouver AB, this is a late fractures. There is a chance of trochanteric migration. So we uses the cable wire to fix that fracture. Then we reduce the fracture by 4-wire technique. We use a 4-wire. There is a trochanteric fracture fragment. We use a 4-wire technique and we fix it. Then we clean out the advance of fracture side. There is a fracture. There is a clean out advance and fix the fracture. And there is a this is a case where this is a non-union of the trochanter side. We using a trochanteric plate to fix it. And there is a fracture of the stem. We are revised with a cemented modular implants. Now the Vancouver AL, early fracture related to if it is a vertical fracture, vertical fracture, we will fix it with circle as well. If it is spiral fracture, we always to revise it with a longer stem. Late fracture, secondary to osteolysis, we have to bone graft it and we fix it with a circle as well. Now Vancouver type B fracture. Type B fracture are 3 types: type B1, B2, B3. B1 fracture, the fractures is around or just below the well fixed stem. The stem is well fixed. That is important. Type B2 fracture is just around below a loose stem. The stem are not fixed. And type 3 fracture is around or just below a stem with poor proximal femoral bone stock. And type C is a fracture well below the stem. Now about the proximal B fracture suite is a revision rate considerably higher due to the loose processes that surgeons thought well fixed. That is the important. Every time surgeons say that a process is stable, so he uses a plate and fixes it. But that is important. So recommended the exploration of the joint to test the prosthetic stability. So most cases require revision. That is the results of fixation, possible versus retention and non-bone terms. So sometimes very easy. There is a proximal fracture. We use a modular and uncemented implant. So this is a cemented. There is a fracture, Vancouver B fracture. We fix it, but that should not be done because there is a breaking of the cemented matter. That fracture it must fail. So principal revision note: not when we are tired, need a team, not unless we have experience and resources. Use a team that bypass the fracture. B2 fracture adjoint fixation is needed. B3 fracture distal fixation, impaction grappling, and allograft prosthetic complex. So what are the options? We have reduced proximal fix the use APC megas processes, use a distal fixation. This is a B2 fracture. This is a B2 fracture. This is the prosthetic is unstable, and we have to replace the prosthetic long stem prosthetic, and we have to fix it with a multiple cable wire and plate. How do we have a extensive lateral approach? and I extended proximally to verify the prosthetic fixation. You have to extend it proximally. Otherwise we have to give the incision that amount, but we have to give the incision so see the hip joint and we see whether prosthesis is stable or not. So technique of reduction, these are 2 fragments and we have to reduce it. Then we reduce it and we have to fix this over a allograft. B3 young and more active patient, we use a modular uncemented implant with a multiple K-wire. And we can use the allograft prosthetic if there is a severe bone deficiency. And older patient, we use a cemented implant. Now the distal vis and Vancouver Cs can use a stud graft salon. We have a lateral plate alone. We can use a 90-degree plates with a plate plus stud graft. What do we need to build? Plates must be of sufficient, must have a sufficient cortices above the fracture. Structure 12 to 16 inch femoral frozen freeze-dried, 18 gauge cable wires, wire twister reduction, forceps and clamps. So this is the stud graft alone. The force 39 of proctor fractures united. We can use a DCB plates, and we have found there is in 18 cases there are 4 non-unions, 2 with a plate failure. We can use a locking plate. Even in locking plate, we have in 18 cases that we find that 4 cases of non-union. So the next cases is that do not treat all the fractures with a plate alone because there is a bending. So what we need, we have to plate one side and put the allograft on the other side so that the fixation will be proper. So we have to put the we have a bilateral cortical allograft only. We have put the allograft on both sides and we fix with the multiple K-wire, multiple SSKM. Now do not create a new stress riser. This is the implant end and this is another. So do not create any. So we have to bypass it by a long implant. Vancouver, see there's a Vancouver says if it is a junctional fracture, we have to remove whole the femur and the total femur. So the conclusion incidence is on most B fracture not at the tip will need revision stem. Distal B and Cs do not just plate laterally, use adjuvant fixation optimally on the medial side and minimize stress concentration. And that will be my last slide. That is the infection management of infection over total hip replacement. In 1960, the infection rate is 1.1 to 12%. In 2000, it is 0.5%, and in primary hospital, it is only 0.06%. So the infection is decreasing. What are the risk factors? There is skin ulceration, rheumatoid arthritis. Patient has a recurrent, a patient has a long-term oral corticosteroid. Then there is other risk factors if the patient is a diabetic, renal infection, patient has a neoplasm, and if there is a tooth extraction within 3 weeks. So infection clinical course, it may be acute, it may be chronic, presenting with generally pain. Then it is associated with swelling, fever, wound breakdown, and drainage. In the less than 3 months of infection after the hip implantation, we will find there is a ESR will be raised 71 millimeter, and the differential count will be 67.7% is a polymorphonucleosides. We have to do the arthrosynthesis there. More than 3 months, then we have a pain, swelling, debrided, active drain. There is active drainage. Erythrocyte 63, WBC count will be raised. Then is a acute late hemorrhage. There is a hematogenous infection. There is a classical symptoms of sepsis because there is a fever, pain, and elevated WCs. So the surgical technique is avoid skin breach, avoid creation of skin flaps, hemostasis, and prolonged operating time. These will increase. So have a proper workup. Proper workup is meant that we have to properly examine the wound. We have to examine the patient. There is a serial radiographs. We have to examine the lab, erythrocyte, CD8, CRP, WBC. We have to do a bone scan. Indium scan is very effective. This is a case of infected. Suppressed tech and gallium more specific, more sensitive, specificity sensory more than 85%. Then the term is called arthrocentesis. That is very helpful. We have to aspirate from the total hip by the needle. And there is a direct, we can do a direct smear, we can do the gram stain, aerobic and anaerobic culture. We can culture the for the acid fast bacilli and also the fungi. Now arthrocentesis is when we suspect an infection. If the differential count we see that total count with that 225,000, protein is low and glucose is low. Now how the host responds, there is a glycocalyx formation and formation of biofilm. Biofilm an important and implant and a devitalized tissue causes chronic disease. Understanding the biofilm is some to logical treatment. Now all bacteria make biofilm. Foreign and devitalized tissue can come to biofilm formation and if exposed to bacteria. Now, what the character is, there is only 15% cells, 85% matrix. Matrix is polysaccharide. Biofilm has a structure, and cell lives in the microecology and communicate. Significance in biofilm states bacteria counts 1000 to 1500 more resistant to antibiotics. In a biofilm state, bacteria express up to 60% new genes which changes the cell wall and or membrane structure. So bacteria becomes drug resistant. So biofilm state significant in osteoarthritis, there is a resistance to antibiotic, biofilm permeable to antibiotic all the way to base the 90 seconds, resistant to WBCs and phagocytosis, and resistant to antibiotics. So biofilm can colonize and grow and over a surface within 4 to 8 days. Prolonged wound drainage should not be allowed. So the treatment of prosthetic joint chronic infection, to be effective, the chronic infection, you must able to the cells. At present time, there is a prosthetic removal and removal all the devitalized tissue. And this is the microorganism. The Staph aureus is the main microorganism in the case of prosthetic joint infection. So the classification is that the early postoperative, late hematogenous, and the chronic. In the early postoperative, we have to do the incision drainage. We can change the modular prop. We can resection of the components and incision if the incision drainage fail. If there is a hematogenous infection, there is the incision drainage, retention of the corner, change the modular part, or we can go for a 2-stage reimplantation if the incision and drain fails. Chronic infection, if there is a chronic, the debridement with antibiotics, there is a streptococcus tablet based, avoid repeated sample, frozen tissue section and suction and drains. Now the 2-stage implantation, this is a chronic and failed and most successful treatment and procedure of choice, and we have also remember the biofilm. Now the 2 stages in the stage 1, there is a complete debridement, 6 weeks, the IV antibiotic, and stage 2 is the reimplant. So the first stage is the removal of the prosthesis, removal of the cement, and we have to thoroughly debride the tissue. Stage 2, create an antibiotic. Stage 1, we create an antibiotic spacer that is impregnated with antibiotics. Then we close the wound. That we have an antibiotic spacer there and close the wound. The antibiotic spacer contain generally tobramycin or vancomycin. Sidal level, the antibiotic spacer, the sidal levels on a spacer to preserve the tissue tension and facilitates implant and wound exposure. And the stage 2 is the reimplantation after antibiotic regime. The serial as before the go we have serial aspiration. We have done a bone scan ESR that the surgical bed is non-infective. Now, if we can do an intraoperative frozen section, and if we find there is a less than 5 polymorphonucleosides, there is a no infection, and if there is a more than 10 molecular hyperfill, there is an infection. So we can do for a research, so remove all components, we can give an effective component. So algorithm is that if the infection is less than 4 weeks, debridement and antibiotics and 6 weeks. If the infection more than, we have a 2-stage implant. So algorithm is that the debridement and antibiotic is success, then it's okay. If no success, we go for 2-stage implant. And so as success and no success, we go for a resection arthroplasty. This is the case number 1. And this is the infection. There is a loosening of the prosthesis. We give antibiotic spacers, and after 6 weeks, we convert a long stem implanted process. This is the case number 2. This is a dislocation with an infection. We remove all the implants and give a antibiotic spacers. After that, we convert a modular, uncemented modular implant. This is the case number 3. This is a severe infection. You can see there is a breaking. Here there is a fracture also in the femur in there. We give a cemented spacer, and we have a long stem processes, custom made. Thank you. This is all about the question. Now, if you have any question. And I have been told giving the lecture only about the revision hip arthroplasty mainly, and what are the advances, not about the basic hip arthroplasty. I think that you all know about the basic hip arthroplasty, so I have been told that giving the lecture on the revision and this complication and what the newer implants we have. Is there any? No, is there no? For lubrication, there is a metal on metal articulation. There is a now has come. There is a what I am telling you that My main problem is the metal early failure is there is a where there is a metal substances are generating, and this metal substance is carcinogenic, so it is contraindicated in the childbearing woman. But now we have a newer metal on metal implants, and there is a fluid film lubrications, there is a polar bearing, and you said there is a less generation of the metal ions, and they also said that metal ions are less bioactive. So that is why you go for a metal on now again the metal on metal has come. Cable is surrounded in the standard. We put the, if there is a fracture is there, we reduce it first and hold it with a 2 or 3 cable wires. Then we ream it. Then we put the implant. After putting the implant, there is some amount of loosening will be there because it is press fit. Then again we put a some of cable wire and we twisted it. And that between the gap will be between the two cable wire will be at least 2 centimeters. Because if the gap is less than 2 centimeters, the periosteum will be devitalized. Because of that, blood supply will be hampered.
So this modular implant for rotation surgery, how successful it is?
It is very successful. Previously, we have only the uncemented non-modular implant. Now we have a modular implant. The modularity that we can change the 360-degree version of 360-degree. That is the biggest modularity. Second, we have a calcar part. We have so if you think that you have to replace the calcar, then you can replace the. If you think that you do not need to replace the calcar, so modularity is very effective. The problem of the modular implant is that there is a fitting, there is a dissociation, there is a dislocation, and there is a breakage. But we in our hospital, they are doing the modular implant last 5 years. There is no such things. And that is very effective. If you use a non-modular implant, you come out say that your neck is short now, and your version is not correct, then what you can do? If you have a modularity, then you can change it.
So from which company do you buy these modular?
Generally, we buy from the Johnson Johnson Dept.
And do you prefer cemented or uncemented fixation for THR?
Now, according to the literature, I have a Australian Joint Registry. They have a 10 years registry, and all the registry says that the cemented implant is far better than the uncemented implant, and there is no question. But whatever the reason, we do not need it, that orthopedic surgeons do not follow the evidence-based surgery. So we are using the uncemented implant. Maximum we are using the uncemented implant.
For THR.
Don't you think that the biological fixation is better?
If the biological fixation is better, it is the best alternative. But according to the literature, according to the registry, say all this is that the cemented implant. Even I am telling you that there is a Swedish registry. They have published and they have said that they have now done all the cemented implant. Last Swedish registry 2004 I have searched, and the amount of total hip replacement, that's 95% hip replacement is cemented. Only the 5% is uncemented. Other areas, that is American and Euro, other countries, that the uncemented implant is much more.
Do you also cement the acetabular component?
No, I never cement acetabular. Now, the problem with acetabular cementation is that the acetabular, when we see the acetabular cementation make a graph, the survival up to 10 years is very good. After 10 years, the acetabular rapidly fall of there is a rapidly fall of the rapidly loosening of the acetabular component. So we generally do the uncemented component.
So the femoral part,
You can do the cemented or uncemented, but in our institution we only do the uncemented processes. In very rare cases we do the cemented processes.
In case of uncemented processes, how do you ensure that you are having implant bone contact all around the implant surface?
Now there is no specific data about it. How you know that your stem is press fit? How that is? Now the Corel has have a literature. They says that when you broaching the femur, when you go to the neck size of the femur, because if your neck size of the femur is quite large, there will be a splitting of fracture of the femur. And they say that if your stem, if you do a neck cut, and if your stem goes, if your broach if your femur goes 2.5 centimeter below that neck cut, then you go for the next size of the femur. How we know that that my rimming is perfect? There we have to hold the femur, and we try to rotate it. And if we find that the whole the limb is rotating, we find that my rimming is perfect. and we remove that remark and we give the uncemented stem, put the uncemented stem.
So you identify the shape of the femur right on the operation table. You don't go on a pre-operative.
Yes. We always do. Every cases. In every cases, my boss, my everyone do a pre-operative templating is must, and every cases we do the Harris hip score of the patient. So the further follow-up it will help us. We always do that. Templating is must for every cases.
They don't say keep at least like 2 or 3 sizes with you on the operating.
No. We have all the sizes. All the sizes are available in our OT. And we have, when we are doing the revision surgery, we have everything. The problem with an allograft, because in Calcutta we have not the facility of getting the allograft. So we have to buy the allograft from the Tata Memorial Hospital, Mumbai. That is the Tata Cancer Hospital. We have to send a request and they will send you the whole femur. And it's very low, the cost is not so high, it is only of the 10,000. You have a whole femur. Only 10,000.
And sir, one small question I have regarding cemented fixation is, so